Okay, we have time for one short question. If anyone wants to collide.
Yeah, I have a short question that you have. You said that your data set is pretty clean, that it, as I understand, was recorded on the same microphone in the similar environment. Have you tried on the test to augment to see how robust your model to some, because for other people that probably will use other microphone, maybe more noise and everything.
Yes, yeah, sure. I totally understand your question. No, we didn't had an opportunity because we don't have any chance to test on another sample because we don't have another data set. Sure, we can add noise to our data set, but I think in this case our model will deals with such case fine too, because if we're going to add, for example, noise of restaurant, street, or cafe, our model will train on it, and after it will predict well. So I'm saying that the condition in this case is still pretty same on the test, on the inference. Okay, on the test, but unfortunately we can't test our model in case of if I'm going to record my own voice. I have no label corresponded to this task. For example, I can test it like in ACR problem when I can detect my speech and convert to the text. I can use my own microphone and test in wild, like testing like in real world. My model, but unfortunately now we don't have this opportunity.
Okay, Evgenia, once again, thank you for your report. So, and we need to move on. I would like to invite the next speaker. It's Alexander Fishkov and together with Maxim Panov, they will present their work titled Scalable Computation of Prediction Intervals for Neural Networks with the matrix sketching. So Alexander, are you here?
Yes, hello. Thank you for the
can you share your screen?
Oh, I'm sorry, yes, of course. Here.
Yeah, looks great. You have 20 minutes, so yeah, feel free.
Okay. This talk will deal with prediction intervals for modern neural network models. So we'll start with why do we need these prediction intervals? We propose to use them as a measure of uncertainty of the model. That means that we want to measure how confident the model is in its output on each new input. It can be implemented as an additional quantitative output. So in terms of regression task, there will be a predicted value and some value on the same scale indicating the uncertainty. Why do we even have uncertainty in machine learning? Well, the two obvious sources of uncertainty are the approximate nature of the methods that we use, meaning that we don't get the true value of parameters, or maybe even the model is not true at all. And also data uncertainty, where sometimes you may have a noisy data set, or just the noise is inherent to how you collect the data. And also another more formal view on uncertainty is that classical machine learning methods usually learn to predict the conditional expectation of output given input, while we are interested in providing the full conditional distribution of output given input. And some applications of uncertainty in machine learning include reinforcement learning, active learning, also in terms of practical application is out of distribution detection and adversarial attacks, as well as some critical applications where human lives are at stake, for example. Next, we'll talk briefly about the definitions. So the prediction interval is just a confidence interval for the future outcome. So it's a random interval that is dependent on the data set, and in case of our prediction model, it is also dependent on the particular point where we want to predict the uncertainty. So it's the level of the interval corresponds to the probability of the future outcome being inside the interval. Okay. The basic setting in our work, we focus on the regression problem, and here we briefly state the classical model with normal and uncorrelated errors. So F is our neural network. Beta are the parameters of the neural network. X is our training. X and Y are our training data, and epsilon is a random noise with fixed but unknown variance. Most commonly, this task is solved by minimizing the squared loss with L2 regularization. So here, lambda is our regularization parameter, and beta star corresponds to the true minimizer. But in our case of the approximate algorithm, we will get beta hat as our trained parameters, and now we would like to also compute the interval. This it corresponds to the classical nonlinear regression formulation in statistics, and so there are methods like delta method that can provide such an interval, or you can derive it with similar arguments using Taylor expansion. So we used the following formula from the literature. So the interval depends on the estimate of the noise variance, the gradient at the query point, and an estimate of the covariance matrix of the parameters. And that's actually the hardest part, because modern neural networks have tons of parameters. So J here corresponds to Jacobian matrix calculated on a training set. So and P is so-called effective number of parameters, and it depends on the estimate of the Hessian. So in all these computations, we don't require anything beside the gradients, but it's still very complex for modern tasks. So what we can do first, we conduct some initial experiments that showed that these methods applied to small networks and small data sets has shown good performance, but the direct application for bigger networks wasn't feasible. So in order to simplify the computation, we first used SVD decomposition to simplify the expression of the estimate of the covariance matrix, and this allows us to use approximate methods in for the task. So for matrix J, it is almost always impossible to store it in memory because it is the size of the training set. And and for this case, we propose to use a streaming approximation of the SVD. There are two related methods called frequent directions and robust frequent directions that are based on matrix sketching. What it means is that they accumulate some they store some smaller matrix and then read the rows of the input matrix one by one and update their approximation. So this allows us to save some space and apply it to our task. Also, we propose the following modification. So since we're interested in matrix sigma, we should focus our attention to retaining the larger singular values of sigma as opposed to singular values of J. So for this, we propose to use the following score function to rank the singular values. It is just a reflection of this formula. So in this way, we can work with the rows of matrix J, but acquire the useful approximation for the matrix sigma. And on the next slide, I present the algorithm. Here is just the update procedure. So it works as follows. You read your data set, your training data set, one example after another, calculate the gradient, which is denoted Ji, and then if our buffer is full, we call actual as SVD routine, and then zero out certain number of singular values and singular vectors depending on this score function that we introduced. So why do we have here 2 times the size so K corresponds to the rank of the approximations that we want to use. So why do we keep 2K rows? This is done in order to limit the number of calls to SVD. So we exchange memory for speed here. And why this particular modification with the score is useful is presented here on this picture. So on x-axis we have just the index of different singular or eigenvalue, and they are sorted in the descending order for matrix J. So for the small data set and problem, we have computed the true SVD decomposition and performed all other calculations. And then we also computed the inverse of sigma, and these computations are represented with dotted lines, and with the solid lines correspond to the specters of our approximations. We used the rank equal to 200, so here k will be equal to 200, and we see that if we have used the original method, then we would focus on the topmost singular values of j, so the leftmost part of the plot, and they will correspond to actually smaller values for sigma inverse. While using our approach, we focus on the largest singular values of sigma, and since this is what we care about, well, also it represents kind of good situation, but still we miss something. So the method is approximate and has limitations. Now for our experiments, first we wanted to compare our method with the exact application of the formulas. We have used the classical UCI regression datasets for this case, and we borrowed the experiment setup from the uncertainty estimation literature, especially I think the papers on dropout and other methods use this setup. So we have used the two-layer network with 15 neurons on each layer, linear review activations, and 20% of the data was for the test set. And everything was repeated 20 times with 20 different seeds. And what we care about in prediction intervals is actually the probability of coverage. So how it is measured on the test set, and basically tell us whether the level of the interval is satisfied. So other important metrics are correlation of the width of the interval with the actual error that the network made, and the width of the interval, since we prefer narrower intervals, but still want the first two metrics also to be reasonable. And last but not the least is the time it took for computation, since we wanted to save resources. And here we see that even with applying our approximation, we still get very good coverage for the intervals very close to the required 95%, and the correlation of the width of the interval with the error is always positive, which is a good thing. And also the time savings are probably visible only on some data sets. I should probably talk more about it. So for CT scans data set, it is 50,000 examples. So that's why it requires a computation of very huge, the use of very huge matrices, and also the year data set is 1 million example data set to predict the year of the song. So it also took tremendous time, and that's why the exact method is almost infeasible in modern networks. So next, I present the same metrics, but compared to the established uncertainty estimation methods for neural networks. We have used dropout and ensembles for these methods work with the same network, and we try to do we try to implement the training procedure as similar as possible, except when the authors in the corresponding papers propose some specific setup. So here we can see that unfortunately the popular dropout method fails to meet the required level of the confidence intervals. And what is more striking is that it even isn't always correlated. The size of the interval isn't always correlated with the actual error. Ensembles is also very good and on par with our method, but in real life it requires much more computational resources. So in our view, this is a good and promising result. The next important part is how to tune hyperparameters of our method. Essentially, the method has one single hyperparameter, is the rank of the approximation that we collect. And in our experiments, first, we should, of course, setting it as high as possible is desirable, but resources may not allow that. Thankfully, if we report...
Alexander, sorry, you have a couple of minutes left.
Yeah, yes, I see. So the first thing, we measured the actual predicted performance in terms of probability of coverage. This is on the plot on the left, and we can see that even with a modest number of rows, the approximations provide valid intervals. But the unfortunate thing is that we grossly underestimate the actual number of effective parameters. But since it's only theoretical interest, it's maybe the practical performance is more important. So to sum up, we recommend to set it as high as your resources allow. And conclusion, so we demonstrate that we achieve comparable performance to existing methods. We can also apply to any pre-trained network. We do not suggest any specific training procedure, and we have a single hyperparameter. The downside is, of course, we want to scale even more. And future work may include extensions to classification, especially because we only can apply to logits in one versus rest setting. And I'm sorry, I'm short on time. I think I stop here and answer questions.
Alexander, thank you. Thank you for your talk. Does or something? Okay, like in order to not set you without the question, I have a small question. So have you, so the problem with all these inverse methods is that you will have eventually a matrix of like size of the training set. And have you tried like the simplest approach to make it batch wise? And like whether will it work or not? Do you get the question?
Unfortunately, not fully. You mean so?
Well, instead of the full training set, just take a batch and perform all the necessary like prediction intervals and stuff for it. or maybe use some anchor points or some other methods.
Oh,
so just to introduce the set for this intervals estimation.
I see. Thank you. It's a good idea. So we didn't try it, but what we use is essentially is very similar. So we also maintain a sort of batch of size k, but we do a little more work and we scan through the full training set in order to select the most useful examples. So in some sense, it is aiming for the same thing to just extract some anchor points. Although I should note that there is no clear correspondence between the actual singular vectors and the rows that produce them. But yeah, it's I think it's in a sense similar.
Okay. Thank you for your answer. So I think we should move on. So Alexander, thank you for your talk once again. And the next talk we'll be listening to is the talk by Ekaterina Kasatkina and Diana Vavilova. Is there anyone from? Oh, so yes. both of you are here, according to the Zoom. Yeah, I see. Can you please share the screen? So their talk. Of a multifunctional service center. So Ekaterina, Diana, you have 20 minutes and 5 minutes for questions. So please start at your leisure.
Thank you. Good day, dear participants of conference. My name is Diana Vavilova. I'm a postgraduate of Kalashnikov State Technical University.
Sorry, Diana, sorry for interrupting you. Can you please make your presentation full screen? So we are recording it and it would be much more profitable for listeners.
Почему?
Yeah, great. We see it now. Sorry.
My name is Diana Vavilova. I'm a postgraduate student of Kalashnikov Technical University. I and Associate Professor Ekaterina Kasatkina present to your attention the results of application of data analysis methods for optimizing the multifunctioning service center operation. The problem of digitalization is actual in Russian Federation, both for automated collection, storage, and processing of information, and for the development of new digital management models and service for the population. Currently, the multifunctional center for the provision of state and municipal services to citizens, abbreviation MFC, is one of the main elements of digital transformation in the country. The quality and timeliness of MFC service provision to population are important criteria for assessing the digitalization level. In addition, the relevance of the study of MFC work optimization is explained by their insufficient bandwidth for reservation through remote services. The regional portal of state and municipal service and the central services center. There is a problem of accessibility to state and municipal services through the MFC, which requires a solution. The purpose of this research is analyzing the MFC operation data to optimize its functioning. The general analysis methodology to optimize the MFCs you see at slide 2. Then analyzing data of on the service volatility, FMR analysis and XYZ analysis are mostly carried out. They allow us to group and classify service depending on the stability of demand. As the MFR analysis results of all MFC services are divided into 3 categories, F, M, and R. XYZ analysis allows us to predict change in service needs with a specific time frame is based on the coefficient of variation evolution. According to the variation coefficient, all services are divided into 3 categories. Category X is a stable demand for the service, minor fluctuation, and higher forecast accuracy. Category Y is known trends in determining the service need, seasonal fluctuation, and average predictive capabilities. Category Z is irregular service demand. Trends are not available, low forecasting accuracy. In practice, organizations use a joint FMR and XYZ classification to optimize their work. The research analyzes the operation of one of MFC in the Udmurt Republic, located in the Первомайский district of Ижевsk city. The MFC operation data initial analysis includes the analysis of services by request frequency. Analysis of the MFC data in Первомайский district showed that 80% of 178 services provided are top 8 basic services. See figure 1. Further analysis of MFC work data assumes the classification of services dependent on the services consumption pattern, XYZ analysis. The MFC services in Первомайский district of the Udmurt Republic included in X category are presented in table 1. It's necessary to bring the stability of its receipt and constant availability of specialists provided for this service at the MFC. Client demand for this service is well predicted. Next, figure 2 show us an example of service forecast from the X group using a trend power law model. Service figure 3 presents an example of the service forecast from the Y group using a multiplicative trend and seasonality model. The Z services group with high demand is characterized with low predictability. This category includes only one service. Seasonal autoregressive integrative moving average models are used to predict Z service. See figure 4. The use of various forecasting methods to assess the need of MFC services help to obtain an accurate summary forecast for all MFC services in a short term. It is shown in figure 5. Figure 5 displays that the dynamics of demand indicator for all MFC services is well described by the combined model with account taken of seasonality and trend. Average relative approximation error is 8.5%. It can also be seen that in a period of April and May 2020, there is a sharp decline in the MFC services received, which is associated with COVID pandemic. The MFC's operation optimization. The MFC operation with talent received remotely can be considered as a multiple queue system with a limited electronic queue. The MQS properties of MFC is the input. Its input services of a Poisson flow of MFC services request with a distribution parameter. The N a number of services channels or windows which can be registered via remote services. Each window can serve only one talent at a time. If there are not 3 talents of the current date, then the talent is a queued electronic entity. The number of places in electronic queue M is limited and determined from the number of services windows N and MFC operating mode. Then optimizing the MFC work, the following restrictions they are taken into account. The maximum wait time in electronic queue is up to 7 calendar days. The minimum window workload should be 90%. The results of solving the optimization problem for MFC of Permysky district in Udmurtia Republic are as follow you see at slide 5. The average talent servicing time is calculated as a weighted average standard time of MFC service provision and is equal 24.7 minutes. With the average service time and MFC operation mode by weekdays, the talent service average intensity by one window per day was calculated 16.2 talents a day. As a result of optimization, it's possible to construct an optimal weekly plan for talents provision for the main MFC services in Permysky district. So we have developed a toolkit for analyzing and optimizing the MFC work. It simulates the MFC operating using the queuing theory. This model assumes that the MFC is multi-channel services center with a limited queue. Using a mathematical model, the service window optimal number is determined with a breakdown into various registration forms. Preliminary registration for the current day, and with a breakdown into service types. By using the MR analysis, we found that top 8 services account for more than 80% of MFC requests in the Permysky district. And in the process of modeling the multi-channel queuing system, it is optimized. It was found that in order to keep the workload of Windows service talents from regional portal of state and municipal services and central service center at the level of not less than 90%, and the registration possibility for no more than a week, it's necessary to allocate 11 windows out of 16 for service talents received through the preliminary registration forward by week. And so in the course of recommendation implementing for optimized MFC work, it was possible to increase the employer efficiently up to 96%, raise the number of talent by 30%, reduce the electronic queue as whereby improve the remote registration availability by 22%, as well as reduce the electronic queue wait time up to 7 days. Thank you for your attention.
Diana, thank you for your talk, for your time to talk. So you took like half the time, and that's I as a chair I fully appreciate it because we have some time like here. So does any of the online participants have the questions to Diana?
I have a question.
Okay, so we have an offline question here.
Okay.
You mentioned that the probability of denial is like 8 to like 1 million, right? In your
Don't hear.
Yeah. So on the side is the final numbers. Can you return to the slide with numbers? One more. Yeah, here.
No.
Okay.
Next one.
Next.
Numbers.
Exactly. The probability of denial is 8 and like 1 million. So my question: you have like 1 million visitors in this MFC? So how did you estimate this number with this precision? It's like PF, it's on the left at the bottom.
I did not understand your question. Maybe
yes, yes, this probability of the denial is a PF 8 times 1 to the power of -6, 10 to the power of -6. So how did this probability was estimated?
Okay. This probability is theoretically from books, books of multi-Q system. It's estimated early from researchers.
Okay. Okay, thank you. So if there are no further questions, I would suggest that we will, in a minute, we will move to the next speaker, who is like standing right here. We have some technical stuff to do. Just a second. Diana, thank you for your talk once again. You can stop sharing screen now. Okay, we have an improvised offline speaker now. So just a second, we will share the screen and open all the stuff. Just a second. Can you see the report? I couldn't check, obviously, offline, unfortunately. So, file. Go.
View.
View. Yeah. And your full screen.
Slideshow.
Okay, so we have the next report from the people from the Skoltech. So Kirill Fedyan will talk about the like dropout, which improves the uncertainty estimation via diversity sampling. Kirill, you have 12 minutes and 3 minutes for the questions.
Okay, hello everybody. Hope the conference going well. As Evgeny said, I'm Kirill Fedyan. I will present our work and tell a little bit about uncertainty estimation in general. We present our work, how did we improve with some diversity sampling. We made this work together with Evgeny Cymbalov, Maxim Panov. So first, what is uncertainty estimation? Basically, machine learning models usually give you some predictions, and sometimes it's useful that you have also estimate the error for this prediction. For example, on the right we have example. We have some true function which is in blue, and we have 4 data points, and we can intuitively understand that where we have a lot of points, the error should be smaller, and in the regions where we don't have a lot of data points, we have bigger error, so the confidence interval would be wider. So ideally, the prediction which is in red should be inside the green bounds. And in this work, we will work with regression tasks and classification tasks. So why it's all that important to estimate the uncertainty? First, it's misclassification detection and error prediction. For example, if you have a model that makes some medical diagnosis and it says that you have a cancer, you would probably want to know how certain it is, because if it's 0.5, it's different if it's almost certainly sure. So another thing is outlier detection, because the real data is always noisy, and also some bad guys could try to attack you, and it's good to have the things that would detect such things, and you can reject to classify or reject to predict. And the last thing is sample efficient training and active learning. If the data labeling is expensive, for example, if you have drug discovery and to label each substance, you need to make some laboratory experiments. It would be nice if you have some weak models that would estimate the most potential things, samples that would improve the quality of user. So it's okay. Now let's talk about some popular models. Actually, the last year there was some big progress, but I'll talk a little bit more classical approaches. The first one is Gaussian processes and Bayesian neural networks. They naturally turn the distribution, and if you have distribution, for example, Gaussian distribution, of course, it has some variance, and you can naturally use it as your uncertainty estimation and error. The problem is that it not always scale great, and also there are many works in this direction, but it's still not there. So some time ago, there was proposed that if you use the same dropouts that you use for regularization, but on inference, in fact, it in some sense approximates the Bayesian networks. You can see the picture on the right. So you basically drop some neurons and you basically get many models. In this case, 5 models. And if you try to estimate the standard deviation between their prediction, then it's somehow relates to the variance. So if the variance low and all the 5 models return the same prediction, you can be more sure in your predictions. And then also was proposed why not to just train 5 models separately. It's actually worked better, but the downside that you need to train and keep like 5 or 10 models. Okay. So another problem is dropouts that you require quite a few of samples. In the original work, it was like thousands, but our practical estimations that like at least 100 forward paths you need, and it's usually not very practical to slow down your model in 100 times. So we start to think what could we do. And we remember one thing, it's actually pretty known that the neurons in the models are often co-correlated, meaning that, for example, on the right is the correlation matrix. What it does meaning that we train some multi-layer network, and for one layer, we recorded on all the values that we had on the validation data set. And then we measured how values on different neurons are related. And what we found that Actually, there are big chunks of the neurons that behave pretty much the same or very similar, right? We have these blocks. So what we decided that maybe we should try to generate dropout binary mask in some smart way that would improve the performance of dropout. For example, it would require less forward passes. So we use the so-called determinantal point processes. It allows to sample more diverse from your data set, or in this case, from neurons. It, for example, uses in web search. If, for example, you have a web query Jaguar, and of course, the car company SEO marketing have a better SEO, and so they would make that all the search would be cars, but animals also could be the target of the search. So what sometimes people use, they use DPP that would try to make the results as diverse as possible. So how technically it works, that you have points, you have some kernel functions that is similarity between the different vectors, and you sample is proportional to the determinant of the correlation matrix. That it's basically not correlation matrix, but the matrix based on this similarity kernel. So what we do, we pretty much replace the Bernoulli sampling in masks, which usually used for dropout, with some more smart sampling, which we done from the determinantal point processes. We also need to use different normalization, because in Bernoulli dropout, you basically have same probability for every neuron, and in our case, we have different probability based on the correlation matrix. So we use Horvitz-Thompson estimator. And it actually somehow works. For example, we estimate on the UCI datasets for regression. In these blocks, it's important the first and the third parts. It's like basic MC dropout and the DPP. And as we can see, first the higher the better. And another thing that in blue it's 10 forward passes, and in green at 100 forward passes. And we see that our DPP-based sampling allowed to converge much faster. It's basically enough 10 forward passes. And second, that the results is much more robust in the sense that it's don't vary this much. Okay, and the metric is log likelihood. Basically, it's a metric that force you to find the compromise between the prediction and the correct variance. So it's penalized for big variance, but it also penalizes if your prediction diverge from true value too much. Okay. Also, we try to make kind of out of distribution samples by splitting the regression data sets. Here we also get pretty big gain. And the last thing that we do, we apply to the computer vision classification tasks. It's MNIST, and even ImageNet. And here we try to make sure that the samples with high accuracy has low uncertainty estimation, and the DPP in our method in orange, it performs this much better. The only thing that the plots is not zero based, so I mean it's impressive, but probably we can make it even better. But here it is. Do you have any questions?
Kirill, thank you for your talk.
Okay.
Please, if somebody online or offline have any questions to Kirill, ask them now. It appears that there are. Oh, okay, Dmitry.
Yeah, I would like to ask maybe one question concerning the slide where the approach was tested. I noticed that the data sets that were used for testing were mainly from image analysis. But is it possible to transfer the same models to other problems? I'm just curious.
Yes, the first thing that regression is what not image analysis. It UCI data sets are just table data. The another thing that with our colleagues from NLP task, we try to apply to the similar approach to NLP and they apply it to the BERT, and it's somehow works. Not perfectly, but it allows some gain and improvement.
Oh, thank you. So it might be a point of further improvement. Maybe, I don't know. Thank you.
Yeah.
Okay, any other questions? So it looks like we don't have any other questions for now. And then I would like to turn to the next speakers. So it's Dmitry Medvedev and Alexander Diakonov. Is like Dmitry or Alexander here?
Yes, yeah, I'm sharing my screen.
Yeah, please share your presentation to us.
Okay.
So Dmitry will be talking about generating synthetic training data using gradient matching and implicit differentiation. So you should have 12 minutes, but we're more than on time. So please feel free. Start at your leisure.
Okay. So hello, my name is Dmitry Medvedev, and I would like to tell you about my article, Learning to Generate Synthetic Training Data Using Gradient Matching and Implicit Differentiation. It was prepared with Alexander Diakonov. So data distillation, general formulation is shown on this slide. So the aim is to train a student, which is denoted as theta, with synthetic data produced by teacher, which parameters are lambda. Training the student theta star, we need to estimate the loss on real data, and then we would like to estimate it with different initial realizations of student. And minimizing this objective, we can get optimal teacher. So this task can be solved with gradient descent methods. So here we show how gradient would look like. So this gradient, also called hypergradient, as teacher parameters are hyperparameters for student training problem. The goal of data distillation is that it can be used in practice, for example, for near architecture search, when we need to train a lot of different neural architectures to choose the best one. If we could produce less data on which model train faster to the best quality on test data, then we could speed up the architecture search. So the first approach was suggested by these authors, and it can be named as backpropagation through the student's learning process. The approach is based on the assumption that the student's learning procedure is differentiable, and these distillation methods has two problems: time and space consuming. To perform a single step of updating Lambda, it's necessary to perform end student optimization steps. And while all intermediate results are kept in memory, I mean trace of student weights. So another approach is to use implicit differentiation based on implicit function theorem. If there was an efficient way to invert this Hessian matrix, we would simply have used this equation after the student has reached a local minima on synthetic dataset. Authors of this approach also suggest to use Newman approximation, taking the first few elements of Newman series and controlling convergence with hyperparameter alpha. So this approach has no problems with memory consumption, since there is no need to store copies of the students, but there's still problem that we need to wait until convergence to local minima, and so there's not a lot of steps of optimizing teaching. The last recent idea is usage of gradient matching, where the problem of distillation has been reformulated. And now the main difference is that we want not only to train the student to achieve a good performance on real data, but also to get such a solution as if it was trained on real data. So capital D denotes distance function, zeta denotes number of optimization steps, and next formula shows that a further reformulation allows us to minimize distance not between weights, but between gradients obtained on batches of synthetic and real data. The distance is cosine distance computed for each student's network layer. And the most interesting detail is that this approach allows us to minimize time we wait until do step for teacher optimization, as we update Lambda after each step of student optimization. That's all. So also in our work, we try to use a generative teaching network. All previous methods for optimizing pixels of images, for example, for distilling classification image task dataset. And in this, with this idea, we can optimize some generator, conditional generator network as teacher, and we show that it can help us to reach more greater quality on test dataset. Here you can note that we control the size of this generative teaching network with a hyperparameter. And here on this slide is the main result. So the main idea of our paper is to distill data using more effective methods as gradient matching and implicit function theorem, implicit differentiation based on implicit function theorem with a generative teaching network. The main result of our paper is on the slide. Using gradient matching method and the correct size for the generator, we could obtain higher quality on the test dataset. We used MNIST classification task as benchmark. The x-axis is images per class of synthetic data. It represents the volume of synthetic dataset. And the y-axis shows the test accuracy achieved with data distilled with generators of different sizes, marked with different K, and also the previous approach, where pixels of images were optimized. It marked as double D. In our experiments, we think that it's fair to distill the data by all methods for the same limited time, as this should be counted in total time spent on new architecture search. And we limit time with 15 minutes of training. And here you can see the detail that increasing images per class, increasing volume of the resulting synthetic dataset. Not all methods increase the resulting performance. It's due to they could not converge due to these limits. So let's explain. The next slide shows more detailed results of distillation with different methods and teachers options. So unroll is backpropagation through the student's learning process. Double D is direct pixel optimization. GTN with R&D is generative teaching network with random input, and GTN with LRN is a generative teaching network with input where input is learned as other parameters of this generator. The best performance obtained by proposed joint usage of gradient matching with GTN. Generator with usage of generator, we obtain more contrast pictures. So in conclusion, we can say that in our paper, we honestly compared the performance of all known methods, limited their running time. Also, we proposed new methods based on the joint usage of generators and memory efficient methods. And also experiments on MIST show the selecting correct size of the generator allows to achieve better performance for gradient matching distillation and improves the generalizability of implicit differentiation distillation. So thank you for attention.
Thank you, Dmitry, for your talk. Does anyone have questions to Dmitry, online or offline? Well, I actually have a few questions. So distillation is a really like hot topic, especially in computer vision. And so the main maybe question is, of course, the scalability of these methods, because while you honestly, like according to the talk, compared the results with like larger data sets or larger networks, because using VGG11 as a teacher network is like not in par with the modern computer vision methods, which use like much larger models.
I think with more resources and with such efficient methods of distillation, we can try to scale on bigger data sets. And this probably would be the future work.
Okay, maybe one more question. So what what matters more, like 2 times larger neural network, like for example in terms of parameters, or 2 times larger, like I mean teacher network, of course, and or 2 times larger data set? So are there any kind of estimates according to these quantities?
I think that if you want to increase your quality, then maybe 2 larger times dataset is great, as 2 times larger neural network is also great. But here in our work, we would like to understand what is the most efficient way to speed up neural architecture search, for example. When we can train a lot neural networks to some normal quality, not maybe the state-of-the-art quality, but we can try to understand which network is we are going to choose from all candidates.
Okay, I see. Thank you. So this actually concludes our session. So like if anyone have any questions to some authors, please feel free to join them in our Telegram chat, asking them questions, or via email or some other means of communication. And as there seems to be not much more than discussed, so I would like to thank all the participants, all the listeners, all the authors for applying to this section, for coming here and presenting their talks. Thank you, and please feel free to join other tracks for other interesting talks. Thank you.
Thank you. But if Dmitry is here, may I ask the last question? I just
sorry, Dmitry.
If Dmitry is here only, I don't know.
It seems that I scared him.
Okay. So I just wanted to ask about the developments, because the developments of that distillation for tabular data, because it was presented last year, as far as I remember, and it seems that the team decided to go to a slightly different path in that direction. But anyway, data distillation, even for tabular data, seems to be an interesting topic, which is not abandoned, I hope. But anyway, I will contact Dmitry then and ask him personally. Thank you.
Yeah, thank you, please. Okay, I think we can then end this section. If or we can have a round table for half an hour if anyone wants to discuss something. Okay, it seems like there are a few volunteers to that. So then please feel free to join other tracks. Thank you.
Thank you, Evgeny, for sharing the track. Thank you to all the participants and all the offers. And this one. And what is this? So that's a torture device, or maybe I just maybe I'm just ignorant about the meaning of the word falanga spelled with F. What is this? Maybe everyone knows this torture device. All right. Okay. Okay.
What is it?
The soles of the feet are beaten. Okay. Okay, I see. And another question, if no one wants to. It really is like promising, and it would be great if we could sort of infer a WordNet-like structure from vector space models, from vector representations trained on raw corpora. But is it really feasible? Like, can we really hope that there is some hierarchical structure in distributional vector spaces? Because all this stuff with analogies. Yeah. Sorry.
Yes, there are some papers by Anna, I forgot, still can, Anna Rogers, yes, by her, and she said that it has been discovered that there are several, there are still among those analogies, among those associates, we can see cohyponyms. So because they are interchangeable in the text. So we take this hierarchical structure from WordNet. So we search for the closest synsets in WordNet. That means, for example, for the word banana, we see the words apple, fruit, etc., as cohyponyms, and say, okay, let's take from the WordNet the parents of these words. Yes. Language models like transformers, I guess yes, they know something. So this is something that we are currently working on, and we want to discover that. Yes, please.
From your examples, it looks like you work with unigrams only. Do you see any predicament or difficulty with including multi-word expressions in this sort of in your methods?
Yes, for the Russian data set we use with unigrams only, but this is just the restriction, the limitation of the data set. For the English language, when we subtract one WordNet version from another, there may be multi-word expression, but they are just joined with underscore. So we work with multi-word expressions in this case, and to get its representation, we average the embeddings of each word. So yes, we work with them.
If I may, there's another one. Which method of aggregating? Which method of aggregating the vectors you think is more effective? You mentioned two: concatenation and averaging. What's the best?
As far as I remember, and maybe as far as I remember, that's it's IME and maybe sometimes SVD. IME actually gets best results. It's averaging. Thank you.
Oh no, we're actually out of schedule right now. Okay.
So as far as understood, graph embeddings did not work pretty well for Russian, but works well for English. Do you have any guidelines or suggestion how to apply it to a new language? So basically you have to starts all experiments around, like from start, or you can just pick the best model from English or from Russian? Do you have any idea on it?
Yeah, thank you for your question. I guess this actually happened that because I showed, as I showed you, like this structure. In English WordNet, there are no structures like that. It's mostly parent-child, parent-child, or many children, one parent. Very rarely there are two parents. So, but here in Russian language, in Russian WordNet, there are very complex structures like that. So maybe this is something that prevents the model, the Russian model, to correctly identify the hypernyms, to correctly identify the structure. So therefore, I would say that if you want to apply some methods to a new language, you should look into the WordNet first and see whether to see its structure. If it's like parent-child, parent-child, and they are not related like that, so it's okay. You may apply graph methods, but for more complex structure like that, those are just not working for some reason. Thank you. Yes.
Taxonomy is a tree-like structure, so it doesn't have loops. And can we get the loops during the inference when we have something like this? Or it's impossible?
It still has loops. It's a tree-like structure, but not a tree structure, actually, because it can have loops, as you can see here. That's maybe not loops, but they are still interrelated. So in this case, yes, it's not like a real tree structure. It's a tree-like structure, but it depends on the language, because WordNet looks like more like a tree than, for example, Russian WordNet. So it would depend. Thank you.
The talk will be about biomedical natural language processing given by Zulfat Miftakhudinov. Zulfat working at Kazan Federal University as a researcher, and also he's a researcher in silica medicine and one of my great co-authors. Let's give Zulfat the word, and please, the floor is yours.
Thank you for introduction. So my name is Zulfat Miftakhudinov, and I work at Kazan Federal University as a researcher and in Silica company, also as a researcher. And and I will present you the work named Drug and Disease Interpretation Learning with Biomedical Entity Representation Transformer, which is actually a set of works devoted to the entity linking problem in biomedical domain. So So let's start with some brief introduction into biomedical NLP. In last years, we can observe the exponential growth of the data in biomedical domain. And the biomedical domain contains different data sources. Among them, we can list the biomedical literature, clinical trials, electronic health records, diagnostic reports, lab notebooks, news records, and social media posts. Each of these data sources contains some valuable information and is just waiting to be extracted and used for some social good reasons or for social good. The biomedical NLP has its own challenges. Among them, we can list the variety of textual subjects. It means that different data sources contains different subjects and can be used for different goals. For example, in social media, we observe user reviews on some drugs, and we can use this information for to extract new adverse effects of the drugs. In biomedical literature, we usually observe some new research on the biomedical domain, and we can see some trends and something else. So the second challenge is a variety of communication styles. It means that in different data sources, we have different languages, different language models. So you can never see something presented in the right side of the slide. In biomedical literature, there's actually something obsessive, and the difference in communication styles usually means different language models, which means the problems with adaptation. The third challenge is language specific to medical context, which means that all the data sources differs from the general domain text. It uses some specific language, drug names, the disease names, and so on. And in practical way, this usually means that you need to use some specific language models like BERT instead of BioBERT, and so on. The other challenges is misspelling and ungrammatical sentences and short telegraphic phrases. They more relevant to the social media. And the last one, abbreviations and acronyms, it's relevant to all the data sources, but mostly it makes a problem in social media because people sometimes find out some new abbreviations. They just use it as they wish, and this causes a lot of problems. So this slide is kind of proven that the social media could be used to extract some new adverse drug reaction effects. On the y-axis, you could see the index value that reflects how often we meet some specific adverse drug reaction. And on the x-axis, we can see the adverse drug reactions. And we consider 3 different data sources. The first one is Twitter. The second one is FHIRS. FHIRS is data source that contain official reports on the adverse drug reactions, and drug information database also is official statistics database. And we can see that except the middle part of the graphic, Twitter almost the same as the official data sources, and so that Twitter almost reflects the same information at the official statistic and could be used to extract some new adverse drug reaction effects. So let's consider the default general information extraction pipeline for the biomedical for the biomedical text processing. The first step in this pipeline is usually some data streaming API, which usually collects the text from the different data sources and collect them into one place. The second step is usually some kind of pre-filtering, where we usually use the classification approach to filter out unrelevant and uninteresting text for us. And the third and fourth ones are named entity recognition and the entity normalization. The named entity recognition finds the spans of interest, and the entity normalization links this found spans to the concepts from the knowledge bases. And additionally, we can include the relation extraction step, but in this presentation, we will consider only the entity normalization problem. So let's pay more detailed information into the entity linking problem in biomedical domain. In example of clinical trials, on the slide you can see 4 clinical trials. Each of them contains condition or disease, and intervention or treatment, and the information about the phase. The task of entity linking is to link the mention, condition or intervention with some concept from the knowledge base. And the feature of the clinical trials data source is that some mentions could be linked with several concepts, and in sometimes mentions could be linked with no concepts at all. The case when the one main mention links with several concepts, we can handle using the named entity recognition, or using some rules to split this mention into parts and link each part separately to the concept. And when we have mentioned doesn't maps to any concept, we can use the threshold-based method, which I will explain later. So let's continue. So the biomedical entity linking also has challenges. It differs from the general domain. The first challenge is that entity linking in biomedical domain is synonym rich. For example, if we consider the concept that's relevant to the aspirin, between the synonyms of aspirin, we can find the acetylsalicylic acid, something like NSC 101, some chemical synonyms. And in general domain, usually can't meet this kind of synonym richness. The second challenge is diversity terminologies. At the right part of the slide, you can see the UMLS. It's main ontology on biomedical domain. UMLS contains several terminologies like mesh, SNOMED, NCBI, and so on. And each terminology is used also for the different purposes. For example, mesh, commonly used to index the biomedical literature. The SNOMED is for clinical repositories. ICD, for example, used for the electronic health records, and so on. The third challenge is diverse subdomains. As I said, we have several data sources like social media, like biomedical literature, and this usually causes the problems because in each data source we have different language models. And in this case, also the fifth one is long tail frequency distribution. This means that 20% of the concepts covers 80% of the data, and the other 80% of the concepts are poorly presented in the data sets. So, and in this situation, when you train the supervised models, you use specific terminology, you use specific domain and you use only the concepts that were presented in your dataset, you usually get models that couldn't normally perform on the different subdomains, on the concepts that were not presented in the training sets, and so on. The first machine learning model that were used for the concept normalization is the classification approach. We also experimented with this approach, but we enriched it with the semantic similarity features. For the entity mention, we have two different representations. One came from the deep neural network models, and the second came from the semantic similarity features, which are based on TF-IDF representations. And then we combine these two representations and just used softmax to get the probability distribution over the concepts. So we experimented with several datasets. We used SNOMED, CADEC, SMM for Health, and PsyTAR datasets. And we find out, of course, that the BERT-based models give the higher performance. And the other interesting thing was that the more sophisticated deep neural network model you use, the less gain you take from the semantic similarity features. So this actually is the example of supervised model that poorly performs on the new domains, on the concepts that were not presented in the training part. And to overcome this problem, we proposed our model that called Dilbert, and it presented on the work named Drug and Disease Interpretation Learning. The code for the implementation code you can find on the GitHub account that presented in the slide. First of all, we focused our attention in this work on clinical trials. And the motivation to use clinical trials was because it's a growing interest of the research and is actually have a poorly structured data and really need to develop some methods to process the clinical trials. During our research, we couldn't find out any datasets, domain specific, and we created our own gold standard dataset, the manually with the manually curated mappings between the mentions and the condition and intervention terminologies. So to map the interventions, we used drug bank terminology, and to map to link the conditions, we used the mesh terminology. Our model Dilbert by design is cross-terminological, and we could use any given terminology without any additional retraining, and it's very fast. It could be used for the real-time inference. We used the triplet learning to train our model. Triplet learning requires three texts. The first one is anchor, which is in our case is just mention. The second text is positive text, which is some synonym of the corresponding concept. The third text is a negative text, which is just any other synonym of any other concept. So when we selected these three texts, we just make closer the positive text to the anchor and make away the negative text from the anchor. And in the result, we get the embedding space where the synonyms of the same concept located grouped together, and the synonyms of the other concepts are located in far away. So the main question when you do the triplet loss training is how to obtain the negative examples. We tried several strategies. We used just random sampling. and random sampling plus parents, where we used the positive examples additionally the parents of the corresponding concept. We also used resampling, also called hard negatives. In this case, we used the model that was trained using the randomly sampled negative examples to obtain the hard negatives. And the last one is resampling plus sublinks, where we additionally, as a negative examples, used the siblings of the corresponding concept. So at the inference time, our model used AIST library, which could be with GPU support, which actually give us a very high speed on inference time to find out the nearest neighbor. And we use pre-computed embedding matrix for our vocabulary. And when we have mention, we just we link it to the nearest concept using the Euclidean distance. So to the evaluation process. In our previous work, which is called fair evaluation in concept normalization, we find out that most of the data sets contain duplicates between train and test parts. And the intersection between train and test part is up to 80%. And we proposed new method to filter out this, to evaluate in these conditions models. We filtered out the test set, we removed this 80% of the duplicates, and we find out that the models usually drop in the performance up to approximately for 15%. And when we made evaluation for the Dilbert model, we used also the same strategies. We used refined test sets. Let's take a look at the data sets that we used in our research. We used 4 data sets: CDR disease dataset, CDR chemical dataset, clinical trials condition, and clinical trials interventions. The thing that should be noted is that clinical trials, that dataset doesn't have any train parts. So we train our model on CDR disease and then evaluate it on the clinical trials condition. And we train our model on CDR chemicals and then evaluate on clinical trials interventions. And the thing is that this CDR disease dataset has medic terminology, and clinical trials condition has mesh terminology. As I mentioned before, the clinical trials data source sometimes has mentions that maps to one concept, that maps to several concepts, and that are mapped to the no concept at all. So we evaluated into sets where we used all the mentions linked to the single concept, and we used the full set to evaluate. As the metric, we used accuracy top 1, and we compared our model with by BERT ranking and the supervised Bayesian model. So the results. The first thing should be noted is that the Bayesian and Dilbert highly outperform the BERT ranking model. And our proposed model, Dilbert, is also highly outperforms on the clinical trials interventions dataset, but slightly outperforms on clinical trials conditions dataset. And here is almost no, there is no statistical difference between the different different strategies of sampling negative examples, but we can see that for the clinical trials condition and the clinical trials interventions, the best strategy was to use random plus 2 or 5 parents. So how to handle the cases where the mention mapped to the no concept at all? We used the threshold-based method. It means we set the threshold, and when we obtain the closest concept, if the distance between the mention and the closest concept is bigger than this threshold, we say that this mention doesn't map to any concept presented in your terminology. And we evaluated 3 strategies to find out optimal threshold. The first one is to set a threshold to the minimum of false positive cases. The second strategy is to set the threshold to the maximum of true positive cases. And the third strategy was to use a weighted average of these first 2 strategies. We evaluated it on the clinical trials interventions data sets. We split our data set into the development and test parts, and repeated this experiment 20 times. The first strategy gave us 79 and 41 accuracy top 1. The second strategy gave us 71 and 77 accuracy top 1, and the first strategy gave us 85 and 73 accuracy top 1. So in the result of this experiment, we would say that the first strategy is the best to use to find the optimal threshold. And the results on the test part, here we considered only Bayes-Bert ranking to compare with Dilbert model. We still have the big difference between the Bayes-Bert ranking model and the Dilbert model in accuracy top 1. But the situation with the optimal strategy to obtain the negative examples is kind of different. For the clinical trials condition, we still have the random plus 5 parents. But for the interventions case, we could see that the best strategy now is just simply use random sampling. But again, there is no statistically significant difference between different types of sampling the negative examples. So we also performed the error analysis. The first one, we find out that in 14 cases out of 99 mentions, we incorrectly mapped our mention to the parent concept or to the child concept. You can see the example of this on the slide. The mentioned brainstem glioma was mapped to the optic glioma by our model, while the correct one was gliomas, and the gliomas is parent of optic glioma. And the second thing that we find out is that the incorrectly mapped mentions usually have the more length than the concepts that were correctly mapped. So conclusions. We have developed a simple and effective Dilbert model that could be used for almost real-time inference. And you can freely change terminology with almost no drops in the performance. We explored several strategies of generating negative examples, but actually we didn't find any statistically significant differences between different strategies. And we performed extensive analysis of our model on 4 datasets. So thank you for your attention. If you have questions.
Please write it in a Zoom chat or write to Zulfat and he will answer it. Unfortunately, we're out of time, so we will skip question session. Let's thank the speaker again, and then we will start the next NLP session in 5 minutes, I guess.
session. I hope everyone can see my slide. So again, here is the session of computer vision, and we are slightly out of schedule, but I believe we will be in schedule after the two first talks. And the first talk will be provided by myself. So let me show you some results about group level emotion recognition in video. So here is the whole title of my presentation: group level recognition in video using deviation of frame features. And yeah, I represent the authors from HSC University. So I divided my presentation into 5 parts. I'll briefly speak about motivation. I provide some best-known papers related to this task, and also I provide our own approach. I will give you introduction to our own approach, some experiment results, and short conclusion. I expect any question at the end of my talk. So here is the motivation. The motivation of this work is based on the appearance of several challenges during the emotion recognition in the wild grand challenge of ICMI conference. So international conference on multimodal interactions. And one of these challenges is devoted to recognition of emotions of a group of people using videos. So here are some video games from the data set. And actually there are, so it's not an emotion like 8 or 7 in basic emotions. So in this challenge, they deal mainly with 3 effects when there are 3 classes, like positive classes, I mean positive emotion, some negative emotion, and some neutral, or I don't know, in some case, so not positive and not so negative at all. So 3 classes, positive, negative, and boundary. And the task is how to predict this emotion based on the video, so the sequence of frames, and it's assumed that we have some emotional labels for the training data set with static images or with dynamic, with video images. And here is the main data set. Here it's a video level group affect data set, GAF. So again, 3 emotions, and these 3 parts of different videos. This is the video labeled by positive label. This is the video some neutral. I mean that there are some positive and negative, some labels, and here is the negative example of negative label of several frames from negative label. Okay, and the task again is, if we have the whole video, and we need to predict the emotion on the effect of this video, one of these 3 classes. And this was a challenge of emotion recognition in the wild last year, and sub-challenge. And there are several main ideas of the participants of this challenge. And let me briefly introduce the main ideas. They are more or less close to each other. So this is the GAFnet. So it's published by the authors of this data set. So at first they provided the data set, and then they provided some baseline. So this is a baseline, and actually even this baseline is really similar to the methods that were proposed during this challenge. So most of these methods are ensemble methods. So you see here there are 3 parts. One of the parts analyzes the whole image, the image at all, is using some neural network. Another part is devoted on the prediction of affect based on the faces. So you detect faces, and then you analyze facial expressions, for example, facial emotions, so I don't know, something like this. And then they used this part of ensemble, and also there are related to analysis of audio features. So, and here are some part of this paper, the ablation study. They show that these parts are necessary. The audio features are not so important, so they are not so, they can provide really high accuracy, but you see that the fusion leads to something like 60%. So it's a rather complex task. You see that there are 3 classes and 61%. So yeah, it's of the baseline. And I will show you that the top performance slightly higher, achieve the score slightly higher than 70%. So it's really complex task. But you see that, for example, face features are close to here. So face features are the most important here. And I will show you later that our main idea is, so our method is mainly based on processing of facial features. So, let me introduce, very briefly introduce the participants, I mean the winners of this challenge, 3 main places. So this is the 3rd place, it's K-injection audio-visual network. So there are some attention mechanisms, there is analysis of audio. There is also a really interesting part from my point of view, analysis of, so they describe the video using some text and then they analyze this text using word embeddings, yes, and some gates recurrent units, something like this. And also the parts are related to analysis of the whole video frames, the audio, attention mechanism, and so on and so forth. So this is the 3rd place. The 2nd place is for spatial temporal fusion. So they provide a huge ensemble with different parts. So one of them is attention, again, attention for faces. So it's a frame attention network, so-called. So you extract faces in each frame, then you extract features, and then you combine them using some attention with 1 or 2 layers. Also, there is really interesting here devoted to analysis of the whole video. It's so using so-called method, slow fast method, and they deal with different frame rates. So they extract frames at low frame rate, they extract frames with high frame rate, and then they analyze them in different parts here, and then they provide some ensemble solution. And actually, here is the whole idea, and you see that the input video is divided into several parts, and all these bounded box, all these rectangles is a single classifier. So you see that there are plenty of different classifiers, like analysis of the whole image, faces, face key points, body, and audio, and so on and so forth. So it's really slow. So it's really slow. It's appropriate maybe for challenges, but it's absolutely inappropriate for real-time processing of videos and analysis of emotions of video of the crowd. And here's a winner of this challenge, and they're really good. As I see, so they propose so-called holistic network, but again, it's an ensemble of several parts. So it's a part devoted to audio processing with open smile features, some emotion recognition of faces, sure, object detection and detected objects, what are objects there, and also analysis of some the whole videos, I don't know, something like this. Yeah, this is part is devoted to the whole videos. We're using TSM networks. So this is the end. Yeah, this is the end of the literature server here. And I should say that okay, what's the main conclusion to this part? So first of all, you see that the participants provided ensembles of many different classifiers. And actually, I didn't show it here, but in the ablation study, they demonstrated that most of the parts of these ensembles are important. So it's if you consider only one single classifier, I mean only one single feature like faces or audio or I don't know, some video, the whole video, and the sequence of frames, it can't reach the performance, or I mean the accuracy of the whole fused model. Yeah, so it's really difficult to create some simple model which can be used and which can be first of all fast, and then which can be really accurate. So actually, this is our task of this is the task of this paper. and our report here, how to solve this task. I mean, how to predict affect using small ensemble or even one classifier, and how to do it efficiently, how to do it fast, how to do it more or less accurate. So for sure, we are not, we don't assume that we can reach the performance, I mean, the accuracy of ensemble of 12 or even, I don't know, 17 classifiers of some participant. Yep. So we want to make it fast because actually these videos should be processed in real time or in close to real time when you need to make a decision about some effect of a crowd or during the meeting, for example, or if you need to analyze the behavior of a group of students listening to some conference. So in all these cases, you need something close to real-time processing. So how we deal with this task? So we mainly use the facial expression recognition and facial emotion analysis. So we used the neural network proposed here. So it's a multitask neural network. It was pre-trained on, first of all, on face identification, and then it's fine-tuned on the facial expression recognition. And the most important part here is that despite the conventional approach for pre-training on face identification, we didn't use central crop with some hairs background or something like this. We use them, we cropped them without any margins. So we ignore some parts, bottom parts probably of the face, and we ignore the hairs. So we mainly concentrate on the face itself, and we mainly concentrate on the facial expression recognition. So in this case, we probably decrease the accuracy of face identification or face recognition, but we hope we can reach the good quality of facial emotion recognition. And in this particular paper, it was shown that yeah, we can obtain really good quality of face expression recognition on static images, for example. Yeah. So and here is the main part of the training model. So you see the facial image, and there is a convolutional neural network. So first of all, it's pre-trained to extract identity features, face identity features, using softmax loss or probably ArcFace. It doesn't matter right here. Then, according to this pipeline, it was fine-tuned. It's partially fine-tuned here for several facial attribute recognition tasks, and then it was most part of this network was fine-tuned on some large data set of emotion recognition to predict emotions from a static image. So this is only for static images. So you have a facial image; it's not a video itself. Yep, and we need to predict this emotion, and we will use such kind of neural network to extract features of faces for our group level emotion recognition task. Okay, so we'll use rather large data set, which is a phase 2 data set, to pre-train the face identity face identification. Yep. So these are the parameters of this data set and some examples. So it's really well known, and it's well known that pre-training on this data set lead to really good quality of face identification. But again, as I said before, we used the margins of these faces, so we didn't consider the background. We didn't consider some hair. Sorry, no hairs. Hairs here. We did consider something here. So we mainly concentrated on the part of the face related to emotions. And this is the data set in which we fine-tuned our network. So this is the well-known AffectNet data set with 8 different emotions. And this is the training data set, which was labeled manually. And here are some examples of the data set. Yep. What's really important here, I should say, that we used so-called sharpness-aware minimization during the training of this network, and we obtained slightly better results if we didn't use it. So let me briefly recall what's the idea of this paper. So the loss function is slightly modified. So this is the loss function, and this loss function is based on some general loss function like cross softmax loss function like cross entropy, weighted cross entropy in this particular case. But here we add some epsilon, some robust. So the main idea of this paper is that they provide some robustness. They require some robustness of the decision, so that if we slightly change the weights of the neural network, then we still obtain rather low value of the loss function. So this is well-known criteria for any method like robust data mining. And then this is the optimal solution in some approximation using Taylor series. And you know probably that this maximum is achieved in the direction of the gradient. So if we use if we minimize it, we need the gradient. So we need this gradient, and it's computed similar in using this approximate equation. And here is the solution of this epsilon, which provides the maximum for this function if we use the Taylor expansion. Okay, and this is the part from this paper, how they demonstrate what's the difference between the conventional, I don't know, I'll classify like Adam or stochastic gradient descent, and here is this sharpest aware minimization technique. So I should say that it really works in many cases, but actually it doesn't work much for transformers, but it really works for convolutional neural network. And for various convolutional neural networks, and that's why we use it, and we observed slightly some improvement in result accuracy. So here is actually the proposed pipeline of, so we use this convolutional network to extract features, and here is the whole pipeline. So we have a video, we extract faces using something like MCCNN or something like this. Then we identify these faces, and then we group them, cluster them, and after that we compute these emotional features. So this part is solved using some face identification network. This part is used using another network like emotional feature extraction. So in our approach, we use this network and fine-tune it on AffectNet dataset and obtain this network. So we have two neural networks. One is used to cluster faces, and another one is used to extract the emotional features. And after that, what we use here, we didn't use attention, or we didn't use some recurrent neural networks because the data set is not so large, and we observed that the more simple solution works better. So it doesn't lead to overfitting, for example. So we concatenate the features, I mean, the individual features of faces using some statistical features. Here are the example of mean STD, but in the final pipeline, we still use only maximum or only one part of these features. And after that, we compute the whole feature. So we compute the features for each face, and then we compute the whole features for the whole video. So in some other way how to distribute it, we can compute the frame-wise features. So this is the features of the frame of all faces in one frame, and after that we compute the video descriptor. So here we will show in our ablation study that simple maximal features will work better, and for computing the video descriptor, we are interested only in standard deviation of these features, of these frame-wise features. So, but for sure we can use so-called stat features and concatenate mean, maximum, standard deviation, and so on and so forth. So here is the whole proposed algorithm. I said that it's based on face detection and is only on facial analysis, so analysis of facials. But actually, we examined some part how to improve the quality if we can analyze, for example, audio. So if the audio modality is available, we can compute some emotional embeddings for audio and using some blending of two classifiers. So this part is optional. And I will show you that I believe that it's not required. It can only it can increase the overall accuracy, but the increase is not so high. So in generally, we can concentrate only on this part. So we can process only face. So here is our experimental results on this GAF dataset. This is the ablation study and the validation accuracy for various features. And so we here is the start features to combine facial embeddings in one frame. And this is how we combine frames in a video. And you see that we have two neural networks. So we're concentrated on fast computations. And that's why we were concentrated on, we train such networks like MobileNet and EfficientNet. And actually, what's really interesting here, I should highlight here that EfficientNet, so MobileNet works slightly better. So right now, after the publication of after the preparation of this paper, we trained another neural network, EfficientNet B2. So this is EfficientNet B0, and we trained EfficientNet B2, and we slightly increased the accuracy when compared to MobileNet. But again, EfficientNet B2 is much more computationally expensive. So I don't. So if we concentrate on the performance, on the running time, then probably the MobileNet is the best choice here. And you see that the best choice here is 68 and 93. I believe 68 and 93 also here, and yeah, and something like this. Okay, so this is the some additional part of this validation accuracy. So this is one classifier, and also this is ablation study of different classifiers. And you see that the best results are obtained just for maximizing the features inside one frame and computing the standard deviation using these features for the whole video. Here is approximately 70%, slightly less than 70%. So you see it's really simple. So you compute the MobileNet features, you extract the features using MobileNet, and then you combine them using maximal statistical function. And after that, you compute the standard deviation of these features, and you obtain the same dimensionality of the feature vector, and you obtain really good quality. So yeah, this is about performance, I mean the running time, and yeah, running time, average running time per one phase for CPU and GPU of some mobile device. Actually, so the idea was how to implement this in mobile device. So you see that it's really it's rather fast, but for sure, if we have plenty of phases, plenty of detected phases, then we need to process all of them. So it's some kind of disadvantage of this approach. And this is a comparison with existing techniques, I mean, with ensembles. So this is ensemble solutions, the best known single models. So here is our part here. So it's better than any existing single model. So it's based on the phase analysis. Slow fast is really good. But if we, for example, take a look at the processing of phases, yeah, you see that it's 64%. It's the best solution of the winner. So they use DenseNet 121. It's more competitive. It's our approach is more computationally efficient, and it's 4%. It has 4% higher accuracy. So it's really good. So this individual classifier works really good. And if we take a look at the ensemble, our ensemble, very simple ensemble with audio features, you see that we increase the accuracy to approximately 72%. So it's yeah, greater than 2% increase. I'm not sure that it's important in all cases. So maybe this performance is more or less appropriate. But nevertheless, if it's possible, why don't do it if we have the possibility to do it? So you see that we're still worse than the top, the winner, which uses this really complex ensemble. But I'm pretty sure that if we add our model for phase processing to this winner, unfortunately they didn't provide their source code, their model. So, but anyway, if we add it, we definitely increase this accuracy because our phase processing is much better, and their phase processing is the most important part of this ensemble. Yep, and for example, we are better, we're slightly, but very slightly, but better than the Fusion of 14 models. We are much better than the third place with the K injection network. We are better than this ensemble of baseline of this challenge. So it's really good results. Here are the confusion matrices of the phases of the processing of phases only. of audio, you see that audio classified not so good, but neutral is more or less the same, but positive is not so good. Yeah, positive is classified really bad performance. And here is our ensemble of our blending. You see that it's still slightly better than these faces. So if we can process faces and audio, let's do it. But if we don't need it, probably even this part is enough. So, okay, here is the conclusion. So we achieved high accuracy when compared to previously known best single models. So we added some robustness to face extraction and alignment. And our approach is based on really simple mobile net architecture, so it can be used on any mobile device and even on some edge devices, so on video surveillance systems and so on and so forth. But for sure, there are some disadvantages. And first of all, it's slightly so it's not so good as the top, but so it's a winner of this challenge. And yeah, there is some future work on how to improve it by using again some ensembles. So as I said, we can change the architecture to efficient net B2 or B3, and we can increase the accuracy. But again, it will be done by decreasing the performance. So thanks for attention. And if someone has some question, I will be glad to answer it. Okay, let me take a look at our time.
Thank you very much for your presentation, Andrei. Do you hear me?
Yeah.
Sure. Can I ask a question? In your conclusion, you stated that your approach could be applied in mobile applications. So my question is, have you already thought of any particular task for mobile applications where your approach could be applied?
Yeah, thanks for this question. Actually, yeah, right now we work on some application which can use partially our approach. So this application is analysis of videos of students, behavior of students listening to some course or something like this. And in many cases, the listeners work on the listen to the course on the mobile device. Yep. And in this case, so they are listeners or students, so they have on the mobile device, and probably it's really important to analyze the performance, to analyze the engagement of students to this to the online lecture, for example. And this is our project, and you know that in many cases it's not desired to move the video of a face to some remote server, and that's why we extract features of each listener on his particular device, and after that we move these features to some laptop, for example, of a teacher, and it can analyze the parts of his lecture which are not so in which there were problems or in which the students were not engaged, for example. Yep. So this part, feature extraction of faces is done directly on the mobile devices of students, of listeners. So we really need to process them on mobile device. Yeah, and that's one of the applications which we work together. I'm pretty sure that there are other applications which really need it.
Thank you very much. Thank you very much.
Okay, so thanks for this question, and I believe we need to move to the next presentation. Yeah. So I will return to the position of the track chair, and I will be glad to ask Evgeny Мясникov to introduce his talk. So Evgeny, you are welcome to share your screen.
Okay, do you see my presentation?
Yeah, we see the PowerPoint. Probably you can press F5. Yep. Or how do you?
Okay.
Yeah, excellent. So go ahead.
Thank you very much for presenting me. My name is Evgeny Vesnikov. I'm from Samara National Research University, and my today's speech is devoted to the dimensionality reduction of hyperspectral data using Hellinger divergence or Hellinger divergence. I would like to start with the notion of hyperspectral image. This is a three-dimensional array or cube having two spatial dimensions and one spectral dimension. The spectral dimensionality of hyperspectral images is very high compared to usual three-channel images. The number of channels in hyperspectral images are hundreds. This high spectral resolution allows us to solve many applied problems with higher quality compared to ordinary images, such as material detection, classification, visualization, outlier detection, and so on. But this high spectral resolution also lead us to increased costs of storage, transmission, processing of such images, and so on. So the elimination of redundancy of hyperspectral images is a very important problem. And this is the topic of today's presentation. To reduce the dimensionality of hyperspectral images, many different techniques have been applied, such as feature selection, unsupervised dimensionality reduction. Both directions have success in this, but dimensionality reduction techniques are more popular as they do not require the labeled set, which are huge and very time consuming. And also these techniques are more stable to change in the scene. Dimensionality reduction techniques usually divided in linear, such as principal component analysis and nonlinear techniques. And the leading technique is the principal component analysis, of course, as it is much more popular. However, nonlinear techniques are also, the popularity of nonlinear techniques are also increasing last years. Nevertheless, they have a number of disadvantages, such as long running times, unable to recover hyperspectral data, source hyperspectral data, and so on. But they capable to deal with nonlinear effects which could happen in hyperspectral images due to, for example, water absorption or multipass light scattering, and so on. And also they are ready to be used with alternative dissimilarity measures, which could be also important in hyperspectral image analysis. We will start with very simple nonlinear mapping technique, which is based on the preservation of pairwise Euclidean distances between points. Here on the right side on the slide, you can see the word dimensionality, which is pointed by dots in three-dimensional space on a surface of a half a cylinder. And the picture in the middle is the result of the principal component analysis. We mapped this data onto two-dimensional surface, and we can see only global two-dimensional structure, which is a curve, and cannot see any local dissimilarities, any local distances between the points. And the nonlinear mapping technique allows us to see both global structure and local structure also. So in this kind of techniques, we usually introduce some data mapping error and use any appropriate optimization technique to reduce this error, for example, gradient descent technique. nonlinear mapping technique could be applied in many different ways. For example, in classification, segmentation, clustering, and also in visualization of hyperspectral images. It is a particular problem because we cannot visualize images with more than 3 channels on our devices. So, for example, we can build such pseudo-color representations where the distances between the points in the formed color space approximate the distances in the source multidimensional hyperspectral space. Also, we can visualize in 3, for example, or 2 dimensions hyperspectral spaces. This is another example. And by the way, we expect that Porian members are located on the in the corners of these point clouds, and Porian members correspond to separate classes or materials which are depicted in the hyperspectral image. In hyperspectral image analysis, researchers apply different dissimilarity measures, not only Euclidean distances, but also spectral angle mapper is quite a popular dissimilarity measure. It was also used in a number of papers, in several papers, with dimensionality reduction techniques. You can see some examples below. Also, the spectral information divergence shows very good results in hyperspectral image analysis. Only several papers used it in hyperspectral dimensionality reduction techniques. You can see these papers on this slide. But there are research which shows that spectral information divergence is quite good in classification and search for spectral signatures in hyperspectral images. But unfortunately, spectral information divergence is not a metric, is not a true metric, and does not satisfy the triangle inequality. And so many techniques which use this feature of metrics cannot be used with spectral information divergence. For example, we cannot use binary space partitioning tricks to accelerate nearest neighbor search and classification. We cannot use some fast clustering techniques, for example, Trimet technique for Kamedoid's algorithm, and so on. That is why this year we suggested to use Hellinger divergence or Hellinger distance to measure the dissimilarity between points in hyperspectral space. And this distance showed very good results, both in the search and the classification of hyperspectral data and in clustering. This distance satisfy all the conditions which we use when we say about true metrics. So it can be applied in binary space partitioning tricks and other techniques and algorithms to accelerate them, and so on. When we would like to build a dimensionality reduction technique with some particular metric or some particular dissimilarity measure, we can consider 2 ways. The first way is quite straight. We can just treat our dissimilarities or our distances or metrics as a dissimilarity metric and use the idea coming from multidimensional scaling and approximate these distances with Euclidean distances in the reduced space. The second way is a bit harder. We can introduce some data mapping error and search for analytical gradient of this error and apply, for example, gradient descent technique or some other technique to minimize this error. For spectral angle mapping dissimilarity measure, there was introduced spectral angle preserving mapping, which is shown in this slide. This is a recurrence equation for searching output coordinates of data points in the resulting space. This particular technique maps the source hyperspectral points onto the unit hypersphere. These are results of this mapping. Similar technique was introduced for spectral information divergence, and it is called spectral divergence preserving mapping. This is a solution for the output coordinates in the output space. And in this paper, we do almost the same. We introduce the data mapping error, search for particular derivatives, and obtain the solution for the output coordinates in the reduced space for Hellinger divergence preserving mapping. Unfortunately, poor gradient descent works very slow. We know it from, for example, neural networks. So here we apply stochastic gradient descent to reduce the computational time and computational complexity of the algorithm. So these pictures show us how the data mapping error changes with iteration, and these numbers shows us how we can accelerate the mapping when we apply stochastic gradient descent. In our experiments, we used two known hyperspectral sensors. The first one is the Andean Pines test site, and the second one is Kennedy Space Center. They both were collected with the AIRS sensor. The first one contains 200 spectral bands after some bands were discarded, and the second one 176 bands. At first, we studied the workability of both approaches. The first approach is the nonlinear mapping based on the approximation of Hellinger divergence by Euclidean distances, and the second approach is the Hellinger divergence preserving mapping. So both approaches works quite good. They reduce the error by an orders of amplitude, but we noticed that the second approach, the Hellinger divergence preserving mapping, works bad when mapping to low dimensionalities, for example, 2 and 3. So they rather cannot be used in visualization of hyperspectral images. These are results of the classification accuracy for the nearest neighbor classifier, built on the top of several dimensionality reduction techniques. The first column corresponds to principal component analysis. The second column corresponds to nonlinear mapping, where we approximate the spectral angles by Euclidean distances. The third column corresponds to spectral information divergence preserving mapping. The fourth one is the nonlinear mapping based on the approximation of Hellinger divergence by Euclidean distances. And the last column is the Hellinger divergence preserving mapping. So two last techniques are proposed in this paper. And I should remind that the main purpose is to replace the spectral divergence, the spectral information divergence with Hellinger divergence to compare our proposed techniques with SDPM. As we see for the Indian Pines image, Hellinger divergence preserving mapping works similar to SDPM. That is, it works best for lower dimensionalities. Here it is, the dimensionality is shown on the horizontal axis. So we obtain very low accuracy. And with the growth of the dimensionality, these techniques show similar results and the best results on this image. On the second image of the case C, they also show similar results. But here we see that the PCA works very bad for the dimensionality up to 20. And the results are substantially lower than for nonlinear techniques, which we used in this paper. So if I have a bit time, I can show one more slide. This is these are preliminary results. The first result is the image obtained using the approximation of Hellinger divergence by Euclidean distances. And I should say that it is quite far from natural. The colors in this image are quite far from natural, but we did not do any additional, any post-processing to linear transform these colors so that they approximate the colors which we used to see on such type of images. So these are preliminary results. So I would like to ask you to understand me. And these two images show the visualization of hyperspectral space using this technique. As we can see, we can obtain, we can see different point clouds colored with different colors coming from, these colors come from true classification of this data. So at least we see that there is some correlation, there is some sense to use these techniques also for these purposes, but this is ongoing work. So thank you very much for your attention. If you have any questions, I would like to answer. Thank you.
Yeah, thanks, Evgeny. Any question? Okay, probably I have a small question to you. So do you have some, have you tried something related with dimensionality reduction related to, I don't know, some autoencoders or some neural networks with unsupervised or semi-supervised pre-training?
Yes, yes. Thank you very much, Andrei, for your question. We indeed have several possibilities in neural network infrastructure to reduce the dimensionality. The first one is both of two are quite old. The first one is autoencoder, which is former auto-associative neural networks. Yes. And the second one is Kohonen neural networks or self-organizing maps. I will start with the second one. It is indeed used for dimensionality reduction. I recall that this is a network in which we have one layer where neurons are placed in the corners of a grid. So if we have one-dimensional grid, then we can reduce to one dimension. For two-dimensional grids, we can reduce to 2 dimensions. But anyway, we obtain a discretized space, discretized output space. So in many papers, researchers use post-processing such as Salmon mapping or so on to map the resulting neurons onto the visualization plane. The first approach you recall is autoencoder. This is a very promising approach, I think, but I see here several issues. The first one is we need to somehow learn the architecture of such network. On the one hand, we can, for example, increase the number of neurons and reduce the error up to close to zero values. But also we lose in aggregation properties of such network. And the time which is needed to solve this task is very high, uncomparable to what we have in the sort of techniques which I discussed in this paper. But autoencoders or auto-associative neural networks have a big advantage over other nonlinear techniques. This advantage is they provide us with both direct and обратный.
Yes.
Yes. With both direct and inverse transformation, which is almost in analytical form, because you have neurons, you have architecture, that means you have functions with weights. So you always can return to the hyperspectral space, the source hyperspectral space, with some small maybe, or maybe big error. So I think this is a direction which is needed to be explored. But also I think that in fact there would be a problem of interpreting the results of this network. I mean, the output of encoder should be somehow interpreted, where this poor signatures should be placed and so on. So I think more research needed to approve that this type of algorithms are useful in this task. Thank you.
Okay, thanks. Any other questions? Okay, probably no questions. So I have just a short comment that you mentioned that there are some problems with using fast approximate nearest neighbor search methods if the dissimilarity is not metric, but there are some libraries like non-metric space library which can be used in this case. So just for your just for your attention. So okay. But it's just a comment. So thanks for presentation.
Thank you.
Here is a link in the chat. Okay, and nevertheless, so I propose that every participants are online for our track. So I propose to skip the coffee break because we are out of schedule and to continue with the next speech. I believe it will be Yulia Ganeva, yep, and the paper devoted to iris person recognition. So if I'm right and Yulia is here, you can present. You can add the presentation and share it. I see Yulia is here, but I can't hear her. Unfortunately. No, Yulia. The question is, we are out of schedule. Can you start right now? Because we actually need to start, had to start 5 minutes ago. You can start, so you're welcome.
Good day, my name is Yulia Ganeva. Today I want to present my report on the topic of development of a method for iris-based person recognition using convolutional neural network. Iris identification is one of the most accurate and reliable biometric identification methods, as the iris texture is remarkably stable over time. On this slide, you can see images and, oh, sorry. 1 second. This is a sclera, this is iris, this is pupil. This slide provides a summary of the selected data set. The NMU-IRIS database was used data set of iris images. The database contains 5 images for the left and right eyes of 35 people, which gives a total 4,050 images. The problem of multi-class classification is being solved where the number of classes is 35. To evaluate the quality of segmentation stage, all database images were manually segmented. This slide show the AIST-based person recognition pipeline that we use in our work. It consists of the following steps: image preprocessing, segmentation, normalization, feature extractions, and classification. In many works, the Daugman method, how transform and other used to segment the iris of the eye. The normalization step in many works is implemented of a transformation of localized region of the iris from a Cartesian coordinate system to a polar coordinate system. To extract feature in many works used Gabor filter, log Gabor filter, Kazan transform, and other. Also, in some work, after feature extractions, used step a data dimensional resolution. And final step is classification. In many works using machine learning algorithms such as support vector machine with other kernels, random forest algorithm, the boost classifier, and the K-nearest neighborhood algorithm. Previously, we proposed a method of the segmentation of iris images using a convolutional neural networks architecture unit. To improve the segmentation quality, we selected the most suitable hyperparameters for training neural network, namely a learning rate and batch size. Learning rate selected from 10 to minus third power, 10 to minus 4 power, and 10 to minus 5 power. And batch size selected from 20, 10, and 30. The most suitable hyperparameters for training neural networks turned out to be a learning rate of 10 to minus 4 power and a batch size of 30. When expanding the training data set, geometric transformation were used, such as random cropping of the image vertically and horizontally, rotating the image by random angles, brightness transformation, and other transformation were used on original images. Also, you can see an example of segmentation on the right part of this slide. Left columns is original images, middle is true mask segmentation, and right is segmentation result using convolutional neural network. In our work, we consider two approach for data normalization. The first approach to normalization was proposed by Daugman. It helps embed people construction dilation. To essence, the approach is to convert a localized structure from a Cartesian coordinate system to a polar coordinate systems. As a result of the conversion, you can see on number 1 this. The second approach is the sequence of the following steps: is cropping of the localized iris and zooms the cropped images to 224 to 224. The number 2 shows the result of this approach. In this work, we study and compared the following feature systems. First feature systems is handcraft features, is traditional filters computer vision, such as 2D Gabor filter, 1D Gabor filters, and 2D low Gabor filters. And deep pitches the procedure for extracting the features representation with convolutional neural networks consists in turning off the last layer in pre-training convolutional networks for iris recognition and passing the data through the modified neural network. After extracting the feature representation, data AI-dimensional reduction steps is additionally introduced. In our work, we used most popular dimensional reduction technique, AI principal component analysis. To solve the classification problem, we use algorithms from machine learning is SVM with linear polynomial radial basis kernel, random forest, and near neighborhood algorithm. Also, we used accuracy metrics for estimation result our methods. Formula presented on this slide. The reported study solves the following task: determine the best normalization techniques, choose the best feature extraction method from the previous slide, estimate the best destination size for dimensional resolution stage, and choose the best classification techniques from the slide. Also, we in process training, we use a cross-validation mechanism was used to train and access the quality of the methods. The data set split into 5 clusters. Each iteration of cross-validation for subset were submitted for training, and 1 cluster used for testing. The averaged accuracy is final accuracy our methods. On this slide, we see first part result experimental research. This result on 2-dimensional Gabor filters was used as the first feature extraction techniques after normalization by meta-Daugman and instruction of the feature representation, the dimensional reduction. 1-dimensional and 2-dimensional low Gabor filters became the next method for feature extraction, and this result with use SVM classificator with linear RBF, sigmoid, and polynomial kernels. This slide presents 2-part result experimental research, and this result with using 2-dimensional Gabor filter, 1-dimensional low Gabor filter, and 2-dimensional low Gabor filter with algorithms random forest, neighborhoods for classification. Considering neural network method for feature extraction and modified pre-training neural networks of the Inception V3 architecture and DenseNet 121. The procedure for these techniques was the following: normalization of the original images by the endowment method with using Inception V3, feature extraction using pre-training model for classification iris, and apply dimensional reduction method. We get this result. The final feature extraction techniques was a pre-training convolutional neural networks of the architecture DenseNet. Normalization was performed by cropping and scaling. All sub segments step were similar of thus with inception V3. The result for neural network based feature systems and SVM algorithms we can see on this slide. And this slide consists the result for neural networks based approach, feature systems, and KNN and random forest algorithms for classification. As can be seen, the best classification quality was provided using DenseNet architecture and amounted 99.78%. In this case, the framing and scaling approach were used normalization. The optimal number of PCA component is 128. And the optimal classifier is support vector machine with sigmoidal kernel, this result. And thank you for your attention.
Okay, thank you. So any question to Yulia? Probably I have some questions. So you say that you use the neural networks pre-trained. So they were pre-trained on ImageNet or on some AIST data set, because there are plenty of AIST data sets, large data sets, you can use them.
Pre-training neural networks on MMPR's data set. We trained this neural network in our previous research. And we use this data set because we have easy access to data set, and we have segmentation masks as a data set not have easy access, and some data sets not have segmentation masks. We previously decision task segmentation.
Yeah, I see, but my question is, did you use the neural network pre-trained on ImageNet?
No.
So you have two data sets.
Yes.
And the first one, which was used to pre-train it, what is the statistics of the data set? So what is the data set used to pre-train the neural network?
We use MMU iris data set.
But it's used for not pre-training. It's used for
not
used for classification.
Yes, for classification.
But it's not pre-training.
Yes, this is previously work. We use some augmentation for dimensionally large data set size.
Okay, and probably my other question, did you compare your results with some existing papers for this data set? Because I see only your own result, I mean, on your experiments. So does anyone work with this data set? Do you have some?
Unfortunately, on this data set, have a small amount of work, and we not compare with another works.
Okay, I see. Any other question? So let's thank Yulia for her presentation. Probably we can move to the next speaker. I believe it will be Ilya Makarov with outfit recommendation using visual similarity. Ilya, are you here? Yeah. Oh, okay.
Yeah, hi everybody. So do you hear me?
Yeah, we can hear you. So you can share your presentation.
Yes, just a moment. So do you feel thin?
Yeah, excellent. Go ahead.
Okay, then I have two talks in a row, basically. So I hope you will not be too bored from listening to me. So the first talk is mostly about computer vision, and we'll talk about our work from HSC about outfit recommendation using visual similarity. So basically, for this problem, we have the purpose, to answer the questions, what item of clothing should be chosen from the proposed one so that it implements the outfit well. So you could say that fashion stylists and designers that try to make an outfit fitting not only visual, some visual properties of human, but also trying to complement each other by some styles, color, I don't know, design elements, combination of different type of clothes and maybe some accessories and so on. And basically, we have two questions to be discussed. So one is if we have some number of clothes or garments which we want to evaluate, so whether they complement each other and could we score this? And second problem is just when we have the current outfit, could we add some last missing detail or last missing garment, and this task is called fill in the blank. So basically, this answer it's to determine the compatibility of a set of clothing items that could be extended by one item, for example, to be complete and compatible with each other. So examples of outfit could be seen here. So for example, you have some clothes, accessories, shoes, bags, and so on. And for example, here are some examples for compatibility prediction. So for example, when you have something like gray, gray, black and white, black and light pink shoes and light pink bag, it gets high compatibility score because usually pink and white is match each other from just stylish point of view. So again, I'm not expert in this field, but I could just say that, watching some movies, you could see this kind of styles quite usable. And for example, having a combination of yellow shirt with a green back and something like brown or dark gray the lower part of the clothes, it gets you very low compatibility score. And for example, also just mixing some shirt with another shirt, it's ridiculous and it's not appearing in data sets. In these cases, they usually omit it and get low score. So basically, there are a lot of approaches that try to tackle this problem. For example, one of the earliest approaches just do pairwise similarity. And the problem is that it lacks overall good looking quality for the outfit. So when you could match every type of object with each other, you could get some very limited number of outfits that match together ideally. But usually you may have needed to fit the current number of garments with some additional ones, and they may not be ideally to each other. There are also approaches based on SAMIS architectures, but they're usually overfitting because there is a lack of data regarding good outfits for this kind of training. And for content-based ranking and recommender system, there were several papers, including papers presented in the AIST conference. So in general, it works good, but lack of balance between session-based and content-based recommendations. So basically, when you're trying to extend your outfit, you may overfit either for user preference or what they are choosing, or you may have overfit, for example, for something which is related only to style components and not tackle overall statistics in general. And there is some back in PDF, but basically it's like there is also approaches based on PLSTM for sequence processing. But the problem is that usually it's like there is no order or sequence in the outfit dataset, so it's hard to say how it should be properly trained. So at least there need some modifications of PLSTM, which are invariant under the order of items, so it will be trained good. So overall, structural and content-based features play a crucial role in this task, and the idea is to use some structural, basically graph representation for outfit compatibility. So in our study, we decided to limit ourselves for visual features alone for garments, and for them we use GoogleNet Inception v3 architecture for extracting garment embeddings. So then for each outfit that could be presented in some stylish form, we extract garments IDs and basically constructed graph which just says that two nodes representing each garment are connected if they appear in some of the outfits. Of course, aligning many outfits could result in overlapping edges. So in these cases, there are two approaches that we also tested. So the simplest approach is just to, I mean, if some combinations appear more than once, then just make them as an edge. And another approach is just to make weights for the edges. So basically more outfits containing pairs of items, and it means like more similar there, and we could weight them. If we go to the fashion outfit datasets, we used Polyvore dataset, which is a popular fashion site that has been used by stylists until it was bought by multi-brand retailer and then was closed. But still, it retains a number of outfits that were created by designers and stylists. So usually, these datasets contain some visual representation, which we don't take into account because that's more about some content stylistic cases for attracting humans. But what we do here, we take images. We don't take any kind of text categories and so on, but just consider visual information alone. We do a number of pre-processing, basically by cleaning categories that are not garments or that are rare or left in outfits which contain at least 3 elements and at most 8 elements. So average number of clothes and accessories in the outfit was 6.2 in the clean data sets. Basically about training details. So we have two tasks. So one is outfit compatibility prediction. So in this case, we take garment embeddings from inception, and then we concatenate them and fill with zeros for empty element positions. So we can see that we have 8 positions at maximum. So like we'll just feed the positions which we don't have any kind of information by zeros, and we train the set using the training set of positive examples. And to create negative examples, we randomly replace one item in each compatible garment with a random clothing item of the same category. For the fill in the blank task, we basically do the following stuff. So we take the positive outfits, mask one element, and add 3 negative samples with less compatibility score for outfit. So the task will be to predict missing positions versus training versus fixed number of negative samples. So basically, I don't think that the current statement for how to solve fill in the blank position is the optimal one, as was mentioned also by reviewers. But in general, I would rather say that if we train the model well for compatibility prediction score, you could also train something like 1 versus all classifiers to predict the proper position of one element, and then you could, for example, consequently apply this kind of model for predicting the best chain of sequences for adding elements to the outfit. Otherwise, you could also do some kind of grid search based on just solving the first task and just trying to fill the empty position with maximizing overall outfit compatibility score. So based on our graph representation, we decided to use already well-known model. So we apply GraphSage graph embeddings, which is basically graph neural networks. It follows the idea that if we have some information in the graph of these clauses that are related to each other based on their simultaneous appearance in some outfit, so we could get some information from the neighbors, and that's pretty much the idea of graph neural network. So we have some aggregation function, which in our case was chosen just taking a variety of embeddings of our neighbors, and the model just learned some weights with concatenated vector of self-representation of a node and aggregated message from their neighbors. Basically, this task could be trained in 2 manners. So one is link prediction on outfit graph, and that's the first loss function. So basically, you want to predict that vertices that are connected to each other have close embeddings, and compared to randomly chosen negative samples, they are far from each other. And if we want to train, for example, in supervised or semi-supervised manner, when we have some compatibility scores, for example, that could be computed by other methods or could be stored, from our data sets and from other approaches, and you could just train via using cross entropy with some regularization of weights, so it will also work out. So for the first task regarding compatibility score, we didn't outperform the best similar approach, which takes information not only from visual but also text and labels, but we were close enough. regarding rock metrics. And for fit B score, we outperform existing approaches. Again, it may be just because we have limited the number of positive and negative samples for this task, but we believe that's a proper direction to study this in the future work, because what we showed that considering this task as classification for missing position is pretty good, and it outperforms significantly some recurrent methods or even CMS networks, which try to consider some metric learning or sequential approaches. So in this case, we show that just considering node classification from the graph point of view and the graph representation show good benefits, but overall compatibility score obtained from these cases may be a little bit lacking compared to more general approaches. And as for visual results, you could see some compatibility scores for different outfits. So, for example, we already show that taking some similar clothes will result to very low compatibility scores. Also, we may see some inconsistency in styles, for example, here, and in general, it's like I would just say that this kind of systems, they could be deployed in production in very easy, straightforward manner. So as soon as you have a number of data and you feel people, designers, stylists to create this kind of information, then you could collect, extract the graph representation, and finally train the model to do predictions like people do. Of course, it makes some bias for overall model, but if you have a lot of people who are doing this kind of stuff, for example, if you know that there is online shop which is called Shane, and there is opportunity for registered account to create these outfits. And thus, just by creating and seeing other creators' outfits, you could buy more clothes in one case, more accessories. I mean, just by buying, so you increase the profit from the shop, and you also get the data what you really like. So it's like could be personalized. Again, we didn't study personalized data for users because we don't have access to this kind of information. But anyway, it's like it's really possible to make it in general working quite good, and also personalized, just paying attention for exact user and outfits that he or she likes the most. So basically, as a conclusion for the first talk, we prove that graph representation of fashion outfit can help build-in fashion recommendations. So we didn't outperform the task of compatibility scoring, but we show that simple aggregating graph of garments is enough to achieve high quality in fit B task, and basically, again, novel attention-based inductive graph neural networks can further improve the quality in downstream tasks. So I would like to thank for listening to the first presentation, and I'm ready to answer your question.
Yeah, okay, thanks, Ilya. Any questions about this topic? Okay, so as usual, I have some questions. So first of all, you mentioned that you extracted features using Inception V3 network. So can you say how do you choose this backbone? Just some ideas why this backbone, not something, I don't know, like visual transformers or efficient nets.
Yeah, I mean, it's like, you know, it's as part of this work was partially a student by bachelor student, and she didn't have access, I mean, to good computational resources. So from this point of view, we just take already pre-trained networks and just test it on our data sets, which perform the best in very simple verification procedures. So in this case, I'm not sure that this is the best option, but I would rather say that it's quite, I mean, it's quite good to experiment with other image embedding techniques, but our idea was in general just by taking some pre-trained model, you could extract meaningful embeddings for garments, even not pre-training on something like deep fashion datasets or again polyvore datasets. And of course, it could be further improved with fine-tuning to exact fashion datasets. It could be improved by choosing more advanced architectures. So our idea was just to prove that we don't need For example, for fit-B task, we don't need to really pay a lot of information to multimodal data, such as labels, text, and images, but we could just build well-working model only based only on visual information alone. And for this kind of thing, I consider that Inception may work quite well because the features that we really need is some kind of texture patterns and also color styles and their consistency across one garment. They're enough to be encoded in this representation to perform well in downstream task.
Okay, thanks. And probably one other questions from me. So you presented actually 2 experiments, yep. In one of them, you have a really good increase. The competitors of accuracy is higher than, I don't know, 9 or something, 10%, yep. And then another experiment, you have slightly a lower quality when compared to competitors. So can you discuss for the range audience of our conference, what is the difference in these experiments, in these experimental settings, and what is so just to understand how good is your method and in what application it can be used? Because
I mean, yeah, in simple words, if you just missed one outfit, so for example, you already buy a lot and you want to miss, I mean, you miss some, I don't know, some hat, for example, or some accessory, or I don't know, you don't know what short to consider that will be fit into your back and your hair, then our methods in fit-B task perform quite good. But regarding overall compatibility score, again, we have non-consistent results, and I mean, we'll lack something in quality because maybe it wasn't properly studied how to do attention in this kind of networks, and whether the weighted component or weighted network representation or unweighted is the best choice here. So I would rather say that predicting for randomly chosen items, predicting their compatibility score is quite hard because the number of positive samples is still lacking compared to all the possible combinations. And there is no much clear scenario how you could generate negative samples. So we just follow procedures that were suggested in other papers, and we receive, I mean, some worse results compared to them. Maybe we need to follow some other procedure for generating negative samples for these outfits and dive into details about how, from the fashion point of view, what really is said to be bad outfit. And from this position, maybe we may also have some improvement of a randomly chosen set of clothes and its scoring.
Yeah. Okay. Thanks. Other questions? Okay.
So basically, if you already choose some close combinations and they are good, so you have style, then we'll be able to predict what will be the last missing option for you. Well, so I would rather say, I mean, if you don't have a style at all, I consider our good results in fit-B also will not help you just from the position of how we train this model. But I would rather say that most people have this kind of style option, but it could be further improved by our model.
So you can use it only even if you forgot to buy 2 things, not 1 but 2 or 3.
Well, yeah, of course you could choose it. I mean, if you could use it in sequential manner, yeah. But still, again, if you miss too much, so for example, if you just start with 2 options, there are too much options how you could complement it, and I'm not sure that this kind of greedy extending procedure will result in the best final outfit.
Okay, thanks. So I propose to move to the next speech, again from you. Yeah, but about a different topic of deep reinforcement learning and wisdom. So yeah, games, and you're welcome.
Okay, so let me again check whether you see my screen.
Yeah.
Okay, perfect. So I would rather say that this talk will be much more technical and dive into details. So we'll talk about transformer-based deep reinforcement learning in wisdom, and this joint work supported by HSE University and also Artificial Intelligence Research Institute. So now I will not dive into details about how reinforcement learning works, and in general, I mean, it's very hard to make a presentation on this topic because you need to take a lot of theory to discuss. But I'll just mostly focus on the main points of our work and what we try to test. So basically, we already know that transformers is novel neural network architecture that's successfully used in many sequential tasks, and many reinforcement learning tasks could be formulated as also modeling a sequence. So basically, you have state, action, and reward, and there are various current papers that try to somehow modify rewards and just train transformers on these sequences of state, action, reward, which learns to some good policies. And in general, it's also interesting to see how you could encode not only these sequences, but also how you should encode the states. And in WISDOM, which is basically environment for 3D first-person shooter, you have consequence screenshots from the game environments. You may or may not have some enemies. And the question is how to encode this information just to efficiently train reinforcement learning agents. And in this work, we combine transformer architecture with reinforcement learning and train them in WISDOM game environment. And we show the comparison of different architecture with respect to convolutional and recurrent models. So basically, regarding WISDOM scenarios, I just placed 3 examples of this scenario. So for example, you have some very basic scenario in which the number of actions is limited. You have defense the center scenario in which your players staying inside one circle, and you can rotate and change the position of your aiming position. You need to kill the enemies that are running to you until you are out of ammo. In the health gathering scenario, you need to collect health packs to survive because there is exit on the floor and your health is constantly draining. And there are much more number of scenarios that I will explain later. So in general, final goal is to, of course, to play as a human in deathmatch scenario when every agent is competing with any other. And this is kind of final goal for all the scenarios, I would say. And what we aim to test that we take A2C reinforcement learning model and try to test different combinations for encoders in this task. So basically, you have transformer, which takes first several number of convolutions, then consequent number of frames that will align just vertically, and after that, I used flattening and position encoding before feeding to transformer layer with attention mechanism. In LSTM, you do similar stuff with starting with convolution layers, but then feeding them to LSTM layers. And finally, for purely convolutional architecture, you add some number of other convolutions, flatten them, and train the final results with some number of fully connected layers. We have two options to discuss. So one is, okay, let's test transformers versus convolutions versus LSTM. And in our base model, again, as I've spoken before, we have input and frames combined vertically that are fed to sequence of convolutional layers and then flattened, producing a single flat vector corresponding to the whole frame. And usually this encoded frame would be considered a single transformer CLS token, similar to how BERT is trained. Thus, the whole input sequence for the transformer would be defined using this temporal dimension. And the second goal is that we have a number of papers on transformers that suggest some different modifications with respect to reinforcement learning and other techniques. And we test different transformers by considering 4 modifications that we'll discuss in details. So I'm originally want to apologize because we have a number of texts discussing this modification. It's very hard to compress them to present all the formulas in simple ways. So the first modification, which is called basically reordered player norm, which allows an identity map from the input of the first encoder layer to the output of the last layer. So basically the idea is the following, that we have near zero layers normalization, which coupled with this reorder procedure allows encoder to pass the input reservation to the actor and critic heads, which are used in reinforcement learning agents. And this kind of information will be more or less unchanged from the model architecture in this case. And this kind of trick allows actor and critic learn Markovian policy at the beginning. So basically learning some simple reactive behaviors much more quickly, and it's quite similar how it works in vision transformers as well. The second modification, which is called gated transformer, reportedly should have stabilized the model and improved its total performance by the use of gated techniques from gated recurrent units. And this gating mechanism just replaces original residual connections. And reportedly in previous studies, it increases the stability of the model, but unfortunately, in our studies, we'll later show that it doesn't affect so much. As it was reported in the simplest environments compared to 3D environment. The third modification is basically, okay, let's consider vision transformers with different number of patches. So if you are not familiar with vision transformers, they basically split the image input images into a square grid of image patches. So basically, let's divide the image by many small patches, and a single patch then will be a separate token providing the spatial dimension. And since we consider not a single frame, but a sequence of last frames, then we should both spatial and temporal information and apply positional encodings. So in this work, we just use very, again, due to computational constraints on our resources, which we need to train our agents. And again, it's like the training number of iterations is measured in tens of millions. So in this work, we just use a simple concatenation of sequences of patches from the consequent frames. Also, we could separate positional embeddings, and it could be possibly computed and combined with different element-wise operations such as summation or maximum or something like this. And finally, the fourth modification kind of without CLS token. So the idea is the following. So you could really remove the CLS token, which is prepended to the input sequence and is fed into the transformer. So basically, prepended this token is the originally intended way to solve classification tasks used on transformers, and especially like in the examples of BERT and vision transformers. And the encoded representation of this token is fed into a feed-forward head of heads, which are then trained for classification or regression tasks. In our cases, this token increases the total sequence length, and its usage is arguably not necessary because in many cases, the last element of the sequence, so basically the current frame, the most recent frame, most likely contains the most useful information for the edges. So for example, in the current frame, some enemy appears, then of course this information will be much more useful compared to the previous frame in which there were no enemy in the vicinity of player 3 or something like this. So our comparison results in the following results. So we have trained all the agents with 20 million of iterations and report mean reward for modification in health gathering scenario. So it's the simplest scenario in which you just need to collect health packs again, trying to survive as long as possible. So in this case, you could see that first of all, our modification are better than baseline model, and usually taking the first modification is better than just taking. So basically, having this residual connections of the input improves the performance of transformer architecture. Then secondly, that switching to gated transformers doesn't affect this model in general at all. Also, we compared that vision transformers with smaller patches perform much worse compared to vision transformers with the larger patches. But the tendency is the following. If you continue to increase the size of patches, in the end, you'll just have something like MLP for the image domain, which are very hard to train. In our case, we also have a number of problems for training these models, and it's very hard to train transformers with large sizes. So basically, in general, it usually slows down the training significantly. And the fourth modification of removing CLS tokens really sped up the training. So basically, for all the other experiments, we just take this modification and consider this one of the most efficient ways to speed up the overall training, considering transformer architecture again when we have constrained resources. Finally, let me discuss some results of comparison transformer, convolution, and LSTM based models in different scenarios. So for health gathering scenario, and again, for all the 5 scenarios that I will discuss, we report max rewards and min rewards. So just to show you the differences between different policies learned by our agents. So you could see that in these cases, convolutional architecture significantly underperform compared to the other cases, and the difference between transformer and LSTM models are almost negligible. So the regional position LSTM learns much better policy compared to transformers. And but that is for maximal reward. If you consider familiar rewards that are more or less report better situations, so in this case, you just say that on average, LSTM and transformers learn temporal component almost the same, but starting from some position, some point, transformer architecture perform much better, and only then later converges to points similar to LSTM. In my way home, which is quite complex scenario in which the agent is randomly positioned inside the similar rooms and need to find the armor to kind of get maximal reward and exit out of the maze. So in these cases, we show that convolutional architecture will and basically LSTM outperform transformer architecture. And it was quite interesting because both LSTM and convolutional encoders provide the behavior for agents, so that it's quite clumsy, try to repeat many actions, and LSTM even may not find at all some policies. But again, transformer behavior may be just from lack of it. If it's opportunity for zero shot or few shot learning, it just couldn't locate itself and ending in repeating just some similar stuff and not trying to properly explore the environment. Maybe just from the lack of data, maybe training with much more number of iterations and random seeds may improve this performance. But in this scenario, we show that transformers slack compared to the other architectures. In the scenario defend the center in which the agent is staying, so we see that transformers significantly outperform those baselines starting from some point. It's also the same thing goes in the deadly corridor setting. So in the deadly corridor setting, you need to go through a straight line, and enemies appears from the left and right sides. So you need to hit them like in first person movie Doom, if you see it. So it's quite similar to this kind of thing. And you could also see that despite the maximal reward are more or less the same with the LSTM models, so in the overall performance, you see that again transformer-based models outperform LSTM based on the scenario. And for convolutional architecture, they do not train at all in this setting, so it means that it's quite hard to distinguish positions of enemies and more or less fixed corridor with shifting positions just by using local meshes based on convolutions. And finally, regarding the main results in this match, unfortunately, we showed that in the most complex scenario, we see some good performance of transformer-based architectures in the initial steps, and they consistently outperform convolutional approaches, but learning LSTM shows the best performance in this match scenario. But it also means that you have basically two positions. When you could, for example, do something like collecting things, trying to do some more or less safety actions, and in this way, transformers are quite good. But for example, during the action stage, in which you need to mostly operate based on temporal components and temporal states, in which you need to locate the enemy, shoot it, also try to move in parallels, trying to not to be hit by bullets and so on. LSTM-based approaches works much better and much faster. So of course, maybe training our models will, it's like much more number of iterations will result into comparable behavior, but still we show that transformers are showing good performance on many scenarios, doesn't outperform basic recurrent approaches, and there is a room and study for further discussion of these results. Finally, if we talking about qualitative results, again, like we show that transformer really significantly outperform many convolutional, in many cases, it's like convolutional encoders. And it's like maybe it's a good point to consider some combinations of convolutions and transformers in general for encoder architecture. And if we consider exact scenarios, I would like also to discuss maybe some agent behaviors in detail. So because it's quite hard to demonstrate this during some pre-recorded sessions, so I will just try to explain this regarding different scenarios. So in health gathering, the agents basically show similar behaviors. Also, transformer model behaves less clumsily than others. Convolutional model sometimes shows some kind of non-optimal behavior, missing nearest health kits, even if they are directly on the straight line where we are going on. And LSTM-based model is less susceptible to this behavior, but still, I mean, overall performance is quite close to each other. In the advantage of the center and density corridor transformer-based approach, they have more economy and ammunition and management than other models. But basically, they shoot more efficiently, having less number of mistakes, and while other behavior patterns are more or less the same. And in my way home, agent does not improve its performance at all during the first 20 million iterations, and even training for 10 millions more, it does not outperform the current approaches. And it's interesting that only for this scenario, our convolutional model outperformed both recurrent and transformer networks. Maybe it's also because learning to navigate the exit in the maze, which has very similar visual features, is better encoded by convolutional architecture rather than recurrent transformer-based architectures. And again, in this match, we have the transformer-based model shows like higher speed of training at the beginning, but then it loses to LSTM-based model with the latter quickly leaps in terms of performance. So as for conclusions, like in terms of qualitative behavior, all agents do show policies that are close to optimal ones in the most complex deathmatch level. I mean, it's still not much superior to the human level. Also, recurrent and transformer models try searching for weapons and power-ups and using them in combat, but they usually do not do it in kind of believable manner, and we wouldn't say that they are quite smart to immediately identify some useful objects compared to how humans play. And of course, like our main results from this preliminary study, that transformers are worth studying for deeper rally. We showed that how different modifications may result in the good or bad performance. And however, there is no unique solutions outperform all the other approaches in all the settings in quite complex scenario. But it's like, especially because we train our agent in distributed manner on constrained resources. So in this case, maybe also interesting to see how different combination A2C, H3C algorithms, so it's synchronous or asynchronous learning, could be combined and improved to further produce novel results in this field if you have an access to computational power for training agents for so long time. So I would thank again for your attention, and I'm ready to answer your questions for the second talk.
Okay, thanks, Ilya. Any questions from the audience? Okay, let me probably start. So my first question is, is it possible, is it still possible to compare your results with someone who also used Wisdom, just to play with different possibilities with reinforcement learning? So what is the frank comparison actually? Can you give me some thoughts?
Yeah, I mean, I would rather say that we have started with not just taking some numbers or plots from the other papers, but we just fairly implemented these 4 modifications and baselines. Basically, the first 2 modifications and baselines, they were already presented in the literature, in particular to different environments and Wisdom as well. So for example, combination of 1 and 2 modifications, they were presented for Wisdom environment. And what we show is that basically, I mean, not all the reported values from other papers are really reproducible in our experiments, especially when we train the model in a distributed manner, so in train the agent in the distributed manner. So basically, I would rather say that we certainly lack compared to DeepMind results with possibilities of combining something like graph neural networks and AlphaMu, AlphaZero, something like this, because they're able to train very large models trains use millions of dollars for training and so on. And in our approaches, we just use very limited resolution, really very limited encoders, and test them out and just compare the results. And even then, comparing mean reward and max reward does not solve the problem, because many agents, they have non-robust behavior. I mean, you could certainly say that it's not human playing, but in many cases and many tasks, there is a hope that the array will somehow be used for making believable bots. So basically, computer players or players under computer control. So in this case, we are nowhere close to good results, despite being able to train the agents that will kill similar by efficiency compared to human players, but their behavior is not smart and not robust.
Okay, thanks. And my other question, so you have several levels in the Wisdom simulation. Yeah, and as far as I understand, you train different models for each level. So you show different charts, and probably it's different models. So as far as I understand, you need to choose the most appropriate model during the real game, or you know pretty well what is the level. So how to deal with the different levels in the same game?
Yeah, so there are various approaches such as curriculum learning or hierarchical reinforcement learning that, for example, try to combine or learn or train the agent on levels with increasing quality, or try to combine and switch between agents trained in different scenarios. But as far as I know, I mean, they result in very good performance in very restricted environments. But when comparing deathmatch scenario in which you need to combine all of them in one model, it's not good to just retrain them, I mean, from scratch or in consequent manner. So not to retrain them from one from another in some consequent manner, but it's better to retrain it from scratch. And this kind of simple scenarios are just used for verification that you are going to the right direction. So if your model could get some useful results on that, then you proceed to this much. If no, then I mean there is no opportunity that you will succeed in training in the most complex environment.
Okay, thanks. Any other questions from anyone? Okay, thanks, Ilya, for this talk.
Thank you.
And we can move to the next speech. As far as I see even two authors for the next paper regarding text capture traversal. Yeah, Valery Terehov and Denis Ishkov are with us. So who will be the presenter, and you can share your screen.
So hello, should I start?
Yeah, we can start. Actually, we have a schedule. Yeah, where it's scheduled. Yeah, nice.
So does full screen is visible?
Yeah, everything nice, so you can start.
Okay, so let's begin then. My name is Denis Ishkov. I'm from Bauman Moscow State Technical University, and my today's speech is devoted to text capture traversal via knowledge distillation of convolutional neural networks, exploring the impact of color channel selection. The aim of the work is to obtain a lightweight model for optical character recognition of text capture, which is capable of working on mobile devices. With the growing popularity of internet resources and social networks around the world, the number of automatic internet programs or bots is growing rapidly. Such bots can perform diverse actions without human interaction. For example, this can be data collection or communication with real people. And the problem is that these bots can slow down the work of the site or even make it bring it to failure. That's why people invented ways or instruments to detect such bots and protect internet resources. And one of these instruments is CAPTCHA. However, most of the existing works in this field investigate the recognition of CAPTCHA with a fixed number of characters on the image, which is currently quite rare and can be seen in practice. There are many ways for bypassing such protections, and one of the popular and most popular one is human-powered recognition services. However, such services lack in speed, and they are also unstable in terms of accuracy because of the human factor. And finally, if we talk about deep learning solutions, computer vision solutions, they usually require a lot of computational power, and that's the reason why they're usually hosted on backend servers and so and similar high power, high spec devices. And so the research carried out in our work allowed us to propose an effective method for training convolutional neural network on noisy labeled data for automatic capture recognition. And also we studied the importance of color channels with the help of learnable linear combination of color channels. So let's start with some simple theory. As you may already know, the word CAPTCHA stands for completely automated public Turing test to tell computers and humans apart. And initially, it is looking like a distorted text in the image. However, now CAPTCHA has evolved into various forms. And with the increase of various protective instruments against bots, bots are also evolved, and so there are also some sort of competition between these two forces. And this results in the creation of more complex capture designs. However, the old classical text capture form is still quite popular and used in many popular sites. In our experiments, we used the certain type of capture, the capture of the social network VKontakte. This capture is presented in two formats, namely normal and hard. Both formats have resolution 130 pixels in width and 50 pixels in height. Distorted elongated symbols, as you can see. And 2 or 4 overlapping lines, depending on the format of the capture. The background of images is covered with ripples in cold tones, and the symbols used for generation is restricted to 21, and for the first symbols, only 6 of them are used for generation. So for collecting a data set, we were using two approaches. Initially, without models, we just download captures by the URLs using a Python script, and in such a way we have collected 2 and 1.5 million copies for normal and hard data sets respectively. The unlabeled images, because they don't have labels, we divide it into, we select small subset of these huge downloaded images and manually labeled it to train some initial models. Also, we resize images to the nearest powers of 2. For training, we used a convolutional recurrent neural network. And actually, we train 2 types of models, large and lightweight, because our goal, final goal, is to get a lightweight model which can work on mobile devices or embedded devices. So for backbone in large model, we use architecture similar to GoogleNet. For activation between layers, we used ReLU. As for recurrent block, we used bidirectional LSTM layers. And after that, there follows fully connected layers and softmax activational function. This large architecture contains 5.5 million parameters for training. As for lightweight model, we use 2 architectures. We tested on 2 architectures, MobileNet and ShuffleNet. There is a typo, actually. And we replaced the recurrent block with some one-dimensional convolutions to speed up some computations, because recurrent layers are known that they can be parallelized. And such architecture contains around 260,000 parameters, 260,000 parameters, and which is 21 times less comparing to a large one. Further, we decided to improve the recognition accuracy of a lightweight model with the help of a relatively novel technique known knowledge distillation. So for a large model, a nickname teacher is introduced. In the case of offline distillation, which we used in our study, its parameters are freezed throughout the training. A lightweight model is referred as a student. Its weights are updated during distillation process. And in addition to the standard loss function, a second term is introduced, which compares the smoothed predictions of a teacher and student. This allows the student to approximate the probability distribution of the teacher's predictions. And as was shown in some previous studies by other authors, this helps to achieve better accuracy for the student. Since images contain text sequences of various lengths, it is proposed to use connectionist temporal classification function. The authors of the original paper have shown that this function is differentiable, and this fact allows us to use it as a loss function, which is very good in our case. And we use this loss function as a standard function, both for training a student and a teacher. As for additional term, we use Kullback-Leibler divergence between smoothed predictions of teacher and student. And the resulting loss for knowledge distillation of student is a weighted sum between these 2 losses. For evaluating, if we speak about evaluating the quality, we use 2 metrics. One of them is the normalized Lowenstein distance between the decoded predictions and the true labels. And another one is the fraction of correct answers, or accuracy, which can be also expressed in terms of the Lowenstein distance. And accuracy we used for evaluating the models after training. Also, during the training process, images with the capture are augmented in online fashion. We apply various transformations, distortions, color jittering, lossy compressions, blurring, noising. For this task, we use a Python library named augmentations, and you can see the full list of used augmentations in the slide. So this slide represents the proposed approach of training a lightweight model on noisy data. Training of the classifier model is proposed to be carried out in an iterative fashion. Here, iteration includes automatic labeling of an additional images, combining them with the initial ones, and training new model from scratch on new larger data set. We should talk about why this process is automated. Actually, the lack of necessity of a person in this process of labeling can be explained by the simple fact that there is a feedback from the site. So in the case when the model recognizes the captcha correctly, the screen form of the captcha disappears. Otherwise, the screen form remains and the image is replaced. And we can utilize this information to understand when the model correctly labels image and then it recognizes it incorrectly. Sorry. The student is trained after achieving the desired quality of the teacher. Teacher labels millions of images that we collected initially without feedback from the site. Yes, so these labelings contain mistakes, and thus the name for this huge corpora of data can be named noisy labeled. And on this noisy huge data set, we train a lightweight model. We have a need in this extended and accurate data set because a small set may not be enough for successful knowledge distillation. As for the importance of RGB channels on the accuracy of this student, we train student 5 times on normal format of captcha with standard loss function on each of the color channels. After that, they evaluate the quality on the holdout set. Each run, we restrict by time. If we say more specific, we restrict it by 3 hours of GPU budget. This method can answer us how which color channel is impact on the quality of the model the best, but can't answer how color channels interact with each other. To do so, we also train pair of channels, for example, on red and blue. Also in our study, we compare obtained results with other color projection methods like training on per pixel maximum value among channels or on NTSC grayscale images. Also, finally, in order to find the optimal linear combination, we implemented the custom neural network layer with 3 learnable parameters, as you can see from the slide. Layer receives RGB image as an input and outputs image with only one color channel. This operation actually is equivalent to applying one convolutional 2-dimensional filter with a kernel size of 1 without bias parameter. And these 3 parameters are initialized with NTSC coefficients and are updated via backpropagation. By taking the magnitude of learned coefficients, we can estimate the importance of each color channel on a specific data set. Here you can see which hardware we used for training And here are the results we obtained. According to the results, it can be seen that the teacher model reaches a quality of about 99% on normal format and 98% on hard format capture. Lightweight models trained according to the previously described method lose to the teacher by 10% and by 20% respectively. At the same time, training with this additional term in the loss function helps to increase the accuracy of the model by a visible margin. The size of the training sample affects the final quality of the model, which is quite intuitive. As for the results, this is the results for normal format. We also have the results for hard format capture. You can see that hard dataset requires more training examples. The saturation zone occurs in a region of 100,000 images versus 20,000 images for a normal one. Also, from the obtained data, we can see that the model starts learning in the region of around several hundred images. So that means it is enough to manually label only a small subset of images and use previously described iterative approach to automatically label and obtain a huge data set. As for estimation of the impact of separate color channels on model's quality, we can conclude that training on red channel gives equal results to training on full color channels. Also, training on grayscale images give similar results as for training on full color channels. And training on mix with mixed layer, we can see that the results are statistically better. Here are actually the learned coefficients for the mixed layer, and we can see that red channel is really indeed has the greatest impact on the given capture dataset. Also, we investigated the case then malicious users can train a smaller model only on this one color channel, and we decided to think about some ways how to prevent it, how to prevent such scenarios. And we also train the same model, the same time budget on hue diversity images. So we randomly change the hue of the image. And these results in what you can see, the magnitudes of channels importances somehow became more uniform. The resulting lightweight models was converted to Onyx model format, which allows us to launch it in browser on the client side. In the browsers, models are executed in the JavaScript programming language. As proof of concept, you can see the demonstration stand, which is shown here, or you can access via this link or QR code. And to sum up, a method of training a lightweight model on inaccurate labels from another model was formed. The influence of the training sample size on the recognition accuracy is studied. The need for color diversity in capture design was identified. Otherwise, there is a vulnerability in capture where malicious users can train a model on one of the most informative color channel. The proposed method allows you to train convolutional neural network models and use them to bypass text capture on low-powered embedded devices. And that's all for my speech. Thanks for your attention. I'll be glad to answer your questions.
Yeah, thanks, Denis. Any questions from anyone?
I have a small question, please. Thank you very much for your interesting presentation. But as I understand, you more played on the dark side, I think. And what do you think are other possibilities to improve the defense on the automatic capture recognition?
So yeah, as we speak about some defense approaches, this text capture thing is quite old actually. And if we speak about Contacte, specifically, this capture was not changed for years. I think for 10 years already. There are some better approaches which is more user-friendly actually. And I think that the approach that uses Yandex is quite good, and the idea of the approach is that instead of making more complex capture, adding more symbols, they log some user activities before and during filling this capture field. Yeah, and if these statistics are not are abnormal, or they are as you can understand, by these additional features, you can build a binary classification model which will tell you when the user is aboard, and then the user is actually a real human. And this information can be utilized to defend and to maybe blocked this bad bots programs which fills the capture in under 1 second, and by other features you can also detect these malicious programs and bots. Do you answer your question?
Thank you. I have a small other question. Have you experimented only with the capture you talked about in your paper, or you also considered other captures from other sites, from other sources? I mean, texture captures. Yes.
Yeah, I understand your question. As I said in the beginning, there are only 21 symbols, and they don't. They have maybe 3 or 4 digits, and not the full English alphabet. So this model only knows these 21 symbols, and if you test it on other captures, it cannot recognize some symbols
yes,
that
I see, but maybe you had some preliminary experiments with other sites, with other captures, or you were.
We actually tested the models trained on normal capture to predict hard capture, and the results was quite bad. I don't remember, about 2% maybe. The recognition ability was dropped significantly. But on the other hand, if we evaluate the model trained on hard data set, which sees from 6 to 7 characters, and we try to predict a normal one, then the drop in accuracy is not so significant. I think it was around 20%. Not so it can be used for predicting more more simpler captures, I think.
Okay, I see. And have you experimented with distortion models? I mean, maybe you have tried to generate these captures yourself.
Oh yeah, actually, at the beginning, then the idea of recognizing capture, then there was a goal to recognize capture. Then it appears. We tried to use synthetic data sets where we generate similar captures, but because of the not so accurate generation, I think, procedure, the difference between with domains, two domains, the real domain and the synthetic domain, can't allow us to get good results, and so we decided to go by other path, by other way, by labeling, manually labeling the original dataset.
Yes, I see, and your answer lead me to the thought that the site should just replace the generating model from time to time to prevent training and bypassing the capture. Do you think so?
Yeah, however, these human-powered services, which are paid, so you pay for recognition, they are robust for these types of rotation of capture. And this will not help for those who will want for no, and the cost of the solution or the way to break these captures, so they'll find a way to bypass it even if you rotate it every day. That's what I think.
Okay, thank you very much.
Yeah, thanks for this fruitful discussion. So actually, I have very short question to you. So as far as I see, your student models still work worse when compared to the teacher model. So the accuracy of the teacher model is actually like an ideal, yeah. And the student model reaches some 90%. So they are 10% worse in accuracy. So my question is, if this is true, then is it still necessary to use lightweight models? Because you know that you can, so when you recognize the captcha incorrectly, then it typically has some delay in viewing the next captcha. So you waste time. So what do you think? Do we need an accurate model which is slightly more difficult, or we need a lightweight student model which is not so accurate and we can waste time just because of our errors, your errors?
So yeah, thank you for the question. If we talk about this trade-off in accuracy and recognition type, and maybe devices requirements, if we talk specifically about contact capture, then they don't have such delay. And as I stated earlier, when you fill this field incorrectly, a new captcha appears immediately without delays. So that's actually also a bad thing about security and protection from bots of Contact. However, yeah, on other resources, I think there are this delay, and I think it's application specific. It depends from what you really want to do. If you are a user and this captcha thing annoy you, then maybe such not such imperfect quality can still be pleasable and good for you. But if you're a bad person, a hacker who have millions of accounts and tries to maybe somehow socially engineered, make some influence on people's maybe ideas and so on, then you can use, and you would want to use a near perfect model. So I think the answer is it depends.
Okay, thanks for presentation. And I believe we can move to the next speaker. Yep, so Alexey Kruzhalov and some thresholding techniques for brain vessels. So Alexey, welcome to share your screen. Yeah, okay, it's perfect. You can start your presentation.
Thank you. Hello, everyone. My name is Kruzhalov Alexey. I'm from Moscow Polytechnic University, and I would like to present you our research analysis of thresholding methods for the segmentation of brain vessels. This work was done in collaboration with Andrei Filipovich, my scientific supervisor. One of the contemporary tasks of computer vision today is development of algorithms for cerebral aneurysm recognition. This task is mainly solved by means of artificial neural networks. And the artificial neural networks training result essentially depends on the data preprocessing. And an important stage of the data preprocessing for fulfillment of the above task is segmentation of cerebral vessels, as the structure of vascular tree is an informative characteristic of an image for aneurysm recognition. Vascular tree segmentation can be performed by threshold segmentation methods with use of a contrast agent, which is perfused into the vessels during angiography. The advantage of the threshold segmentation methods is possibility to get acceptable results with minimum requirements to computational resources. So the aim of this work is to investigate the effectiveness of threshold segmentation methods concerning the problem of segmenting cerebral vessels based on rotational angiography results to select the most appropriate method for data preprocessing for use in developing an automated system for detecting cerebral aneurysms. In this study, we use the data published within the framework of the Cerebral Aneurysm Detection Challenge, CADA. The data were obtained with Axiom Artis angiographic system of the C-arm type. The data set includes 110 images, and for each image, there is a segmentation mask of regions of interest. Image size and voxel size are presented on this slide. In this study, we considered the following thresholding methods: Otsus method, Jens thresholding method, triangle method, and Savula method. The first three are global methods, and the last one is local. We have segmentation masks for cerebral vascular aneurysms. So one of the criteria for evaluating the quality of solving the problem under consideration was the value of the intersection of the selected region with the region of interest. It is the first equation on the slide. In addition to maximizing the intersection, we are interested in ensuring that the selected area covers the minimum number of voxels unrelated to vessels. So we have no way to directly calculate the number of false positives since we do not have a segmentation mask for the vascular network. However, we can estimate the volume of the selected area without the area of the interest. It is the second equation presented on this slide. Since the area corresponding to the vascular network must be connected, it is proposed to use the selection of the largest connected area after binarization in order to assess the statistical significance of the allocation of the largest connected area. The Wilcoxon test was used, and the null hypothesis of the test is that the distribution of differences between samples D is symmetric with respect to 0. And to compare the results obtained with various thresholding methods, it is proposed to use the Friedman test. This slide shows the results of applying various binarization methods to the analyzed data. The column Wilcoxon test contains the values of test statistic W and their corresponding p-values calculated for each method according to the intersection metric. The samples to be compared are the samples obtained with use of the selection of the largest connected area and without it. As you can see, we have insufficient grounds for rejecting the null hypothesis at the level of significance of 0.05 only for the Otsus method and triangle method. For the second metric, we obtain statistically significant results for all methods. For a subsequent comparison, we used the values of the target metrics obtained using the selection of the largest connected region. And for a visual interpretation of the results obtained, we built a box plot for the intersection metric distributions. And the diagram shows that the largest median value and the smallest spread of values relative to it are obtained for the triangle method, and the largest number of outliers is obtained for a Savula method, and that's why it was excluded from the subsequent consideration. And the Friedman test was used to compare these methods, and at the level of significance 0.05, there are sufficient grounds for rejecting the null hypothesis. And in order to find out which methods produce statistically significant differences between their results, pairwise comparisons were performed. And based on the results obtained, we can say that statistically significant differences are present between all pairs of the considered methods. And since the triangle method showed the best results, we can conclude that the use of this method for the solution of the problem is most preferable. And to confirm the results obtained, we carried out an analysis of the operation of the considered algorithm on a test image. We took as a test image a slice of the original image, which included a region of interest. This slide shows examples of the operation of the analyzed algorithms on a test image. The first line shows results before the selection of the largest connected area. And the second line shows the results after that. From the examples given, it can be seen that the Otsus and Jens method identified only large vessels with high contrast. And triangle method turned out to be more sensitive to the selection of the less contrasting small vessels, but when using it, some noise components are also highlighted, which are removed after the selection of the largest connected area. To evaluate the structure of the selected region in the volume, 3D reconstructions of the regions obtained based on various algorithms were constructed using the 3D slicer program. And in general, we can say that they confirm the previously made observations that the Otsus and Jens methods mainly delineate large vessels with high contrast, and the triangle method makes it possible to select a wider vascular network, including low contrast vessels of small size. Based on the results of the analysis, it was concluded that among the considered methods, the most suitable is triangle method with the subsequent allocation of the largest connected area. This method turned out to be most sensitive to the isolation of low contrast vessels of small size, and therefore it allows for obtaining a more complete picture of the vascular network structure. And also we can say that vessel segmentation can be used as a data preprocessing method in classical convolutional neural networks, and also for development of more complicated graph models. And I can say that I'm currently working on development of an algorithm for cerebral aneurysm recognition, and the preliminary results of my recent experiments show that the proposed data preprocessing method allows to make an artificial neural network training process more stable and to get higher results from the perspective of recognition accuracy if compared with the used classical methods of preprocessing, such as normalization or standardization. Thank you for your attention. I will be glad to answer your questions.
Okay, thanks. So any questions from anyone? Probably I have some questions to you. So first of all, could you clarify the choice of the thresholding techniques in your work? So I mean, there are plenty of image binarization methods, including something with deep learning, I don't know, some deep neural networks and so on. So what, how did you choose these techniques that you compared them? So what's some ideas from this part?
Most of the papers dedicated to solving this task is used neural networks as the main algorithm. But there is a lack of data sets for vessel segmentation that are available in public domain, and in most of the works, authors use their own data. And in my work, task of vessels segmentation considered as one of the stages of data preprocessing for aneurysm recognition. So it's not the main task for me. So I consider these methods as a preprocessing method that must be and fully automated. They must not require interaction from user. And as I said before, I have no labeled data to train a neural network. So the main idea why I decided to choose thresholding methods was to investigate which results I can get with it. Maybe it would be sufficient for my purpose. And in this case, there will no be necessary to use more complex method that requires more computational resources, for example.
Okay, thanks. I see. So you say that you have only preliminary results, I mean, in the downstream task of classification of these vessels. But anyway, so you say that there are some increase in accuracy by using your this thresholding with triangle technique, for example. So, but you say that okay, it's better than use other pre-training. But do you have some feeling about comparison with existing other methods that probably are more smart than training the neural network? I don't know, ensemble. So I don't some existing methods from existing papers.
Do you mean methods for pre-training?
I mean for the whole task. I mean for the whole task, because you say that you are interested in classifying of it. So again, I see that it's you say that you have on the preliminary results, but nevertheless, can you share? So even your preliminary results are comparable with existing results for this downstream task. I mean for the classification of these vessels for this data set, for this particular data set which you used.
Mm-hmm.
Or you are far from them? That is my question.
Thank you. I can say that I have tried to use one of the preprocessing method that was proposed in one of the papers that uses the same data, and there was proposed just to select threshold value manually and just limit the intensity value of the image to this value. So when I tried to do so, I found that learning process was unstable. I tried to learn my network on random patches from original image because it's pretty huge and I use 3D convolutions, and so I have memory limitations. And when I tried to extract these patches where a region of interest is placed on the center, the learning process was okay. And when I tried to use different sampling strategy, for example, to extract patches with no guarantee that the region of interest will be on the center, it may be on the corner or something, or take different location. And then I got problems with vanishing gradients. My learning process just stopped. And after I apply thresholding, there was no such problem. And additionally, I added augmentations and it was okay. Maybe it can relate to optimization algorithm parameters, for example, because I perform this comparison using the same hyperparameters to eliminate the effect of this factor. So maybe then I can say that thresholding is less sensitive to using more large learning rate values, for example, and something like this. As I said, it's just preliminary results, and I haven't performed systematic comparison yet.
So, okay, thanks. Other questions? Yeah, well, thanks, Alexei, for your presentation, for your answers. And I believe we can close our computer vision track of the AIST conference. So I cordially thank everyone, our authors, the listeners of our track who were with us today. So thanks everyone, and let's move back to the main track, and let's visit AIST tomorrow. So thanks and bye.